Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I teach a variety of undergraduate game design and development courses. I'm also the program director for our Bachelor of Innovation in Game Design and Development. I spent 5.5 years in a company named Peak Game Studios that I formed with my two sons, and now I do my game development in my one-man shop, Burning Teddy. This is a 5-week course, and in the first 4 weeks you'll learn bunches of new material, and then in the final week you'll complete your last peer review. There are 4 peer reviews in the course, and they're each worth 25%, so they constitute your entire grade in the course. I have provided a number of exercises as well, and even though they're not worth any points, they are good practice. Because this is the 4th course in the specialization, I expect you to have a bunch of prerequisite C# knowledge. Instead of going through this list, I'll ask you to pause the video and take a look at this list, and when you're ready, unpause the video. I also expect you to have a bunch of prerequisite Unity knowledge, so again, pause the video to take a look at the list and then move on. In this course, we'll do a number of different lessons. We'll do the getting started, which you're doing right now, and then we'll look at dynamic arrays, which are much like the list class from the System Collections generic namespace, and we'll also take a look at algorithm analysis, which lets us quantify the complexity of operations on different data structures. In the second module, we'll look at linked lists and graphs, and then in the third module, we'll look at stacks, queues, and trees. In the final module of new material, we'll look at design patterns, and then finally in the finishing up module, I will actually, tell you you've done a great job and tell you how far you've come and encourage you to take the last course in the specialization. This course is obviously the 4th course in the specialization, so it builds on the knowledge that you've been accumulating through the first 3 courses. And the topics in this course are based on part of the 2nd programming course at UCCS for game developers, although I will admit it includes more material than I include in that course. As always, if you need help, you should go to the forums, and if you can't find help there, you should surf the web, and hopefully you'll get some help there to work through the problems you're running into. In this lecture, I'll show you how to navigate a Coursera course, and our example course is the first course in the C# Programming for Unity Game Development specialization, but really it doesn't matter. All the courses that I do on Coursera have pretty much the same structure. So let's go wander our way through the course. Here we are on the home page for the course. If you click on a particular week in the navigation bar on the left, you come to the content for that week, and so you can see all the lectures and readings and everything for that week, including the peer graded assignment. We'll have a peer graded assignment every week except the last one. I'm going to click on one of these lectures, and I immediately paused the lecture. I picked this one because I wanted to show you that below the video for the lecture, there are downloads that I provide to you, so I always give you the slides for the video lecture, but I also might give you some additional information. For this particular video lecture, I give you a copy of the appendix of the book to show you how to set up your development environment for MonoDevelop or for Visual Studio. You'll watch the video about picking your development environment, and you'll pick which development environment you want to use. I will also point out that I write a lot of code in the lectures, and I'm not allowed to attach zip files to particular lectures. So for each lesson that includes code, so this your first C# code lesson includes code, I provide a reading that provides all the lecture code for that particular lesson. So you can go here and download zip files that have the lecture code in them, so you can access that code and look at it and so on. In the grades portion of the navigation bar, you can see your grade on all the graded assignments in the course. The discussion forums are places where you can go to post questions and answers if you want to help your fellow learners as people work through the course material together. If you click on a particular week, you will see that you can just post a new thread for this week for sort of general discussion about the topics in the week. But there are also sub-forums here on the right for the peer review that you'll be doing for this particular week, and each of the exercises that are included in the week as well. So the discussion forums are a good place to go to actually interact with each other as you work through the course material. So there you have it. That's how you access the content and look at your grades and access the discussion forums, which are generally a pretty active area of the courses that I teach on Coursera. So there you have it. That's how you navigate the Coursera courses that I provide on Coursera. This is the totally optional, don't watch it if you don't want to, meet the instructor lecture. I'm Tim, Dr. T. Shamillard, and I grew up in a small town in southeastern Massachusetts named Norton. And after high school, I went off to Georgia Tech to pursue a bachelor's in electrical engineering degree, but I was only at Georgia Tech for a year. So if you'd like, pause the video and guess for why I only stayed for a year, and then continue. As one of my past students said, I left for the love of a good woman. So my girlfriend was in Massachusetts, Georgia Tech is in Atlanta, Georgia, and that was too far for me. So I spent about a year and a half putting stuff into boxes and handing it to the UPS guy. And then I enlisted in the U.S. Air Force, went off to basic training, went to technical training school, and after about 4 months in the Air Force, I got married. So pause the lecture again if you'd like to decide whether that was the same girl I left Georgia Tech for or somebody else. The answer is, it is in fact the same woman and we are still married. So here we are in the Air Force. We went off to Omaha, Nebraska for our first tour. And then after 16 months, the Air Force decided to send me to school full-time to pursue a bachelor's degree in electrical engineering at Georgia Tech. So I did get to finish that degree at Georgia Tech in electrical engineering. And then I went off to officer training school and got my commission as an Air Force officer. Our first assignment in the Air Force was at Los Angeles Air Force Base, where I spent 4 years managing contractors writing software to help us fly satellites. Particularly orbital software was my general area of expertise. We had our first 2 children, both boys, while we were in Los Angeles. And I also pursued my master's degree in computer engineering at the University of Southern California, going to school nights. Finished that tour after 4 years and went off to the U.S. Air Force Academy, where I taught undergraduate computer science courses for 2 years. Now, the Air Force Academy is usually a 4-year tour, but I only spent 2 years there. So if you'd like to pause the lecture video again and try to guess why I only spent 2 years, go ahead and do so. The answer is the Air Force decided to send me off to UMass Amherst to pursue a doctorate. So I am in fact a doctor of computer science, so I don't actually help people. And my entire family loved the part in Treasure Planet, the movie, where there's a non-medical doctor and he is trying to help somebody who's injured, and he says, I just sit here and I'm useless. And I saw that movie with my entire family at the movie theater, and at that line, every single person leaned over and looked at me. So everyone knows I'm a doctor, just not a real doctor. Okay, so I finished off that degree and went back to the Air Force Academy for that full 4-year tour that I should have had in the first place. And then my final assignment was to Washington, D.C., where I spent a couple of years managing contractors, developing web applications, and the databases that support those web applications. And then I retired from the Air Force. So I've been at the University of Colorado at Colorado Springs since 2003, and I've taught a variety of courses, including graduate level software engineering courses, undergraduate computer science courses, and undergraduate game design and development courses, all of which I created from scratch. And in fact, we now have a Bachelor of Innovation in Game Design and Development, and I teach many of the beginning and the final course in that particular program, and I'm the program director for that program. So at this point, I exclusively teach game development courses. I also spent a year and a half as an indie game developer in a company that I formed with my two sons, and that's Peak Game Studios. And we did a number of games both on speculation and on contract. So here are the games we built on speculation. The two images on the left are a game called Ket that's based on an actual board game. So we got the license from the board game manufacturer. And you can think of this as chess with lasers. And you can actually download a free version of this game at this point from the Burning Teddy website. I'll talk about Burning Teddy soon. The other screenshot from the upper right is for a game that we didn't quite finish as we shut down the company once my sons sort of grew up and moved on to do other things. And that game is called Battle Paddles. And you should think of this as Pong with weapons, because that's sort of the big idea behind that game. We didn't quite finish it, but we'll get back to that game as well. So on this slide are the games that we built under contract. So as a company, we went and we got a contract to build some games, and we actually got paid to build them, and that was awesome. So the two on the left are for educational games for 8th graders. The one all the way to the left was a set of 4 mini games to teach about physics. And the title of that group of mini games was Physics with Neat Details. And if you think of the acronym for that, it's PWND. And so, of course, a little tongue-in-cheek game development, of course. And the lower one was to teach 8th graders about robotics. So they would configure a robot with various attachments to go complete a number of missions. Again, there were a few mini games to do. The upper right one is something called Colorado History Arcade. We got a contract to teach 4th graders about Colorado history, and that game was deployed on the Pikes Peak Library District website. So all of the games we built as a company, except for the Colorado History Arcade game, were using C#. We happened to use XNA Game Studio to do that. But now, of course, we've moved on to Unity. The company hasn't, but I have. And so that brings us to this next slide, where I tell you I now have a small company, and by small I mean just me, called Burning Teddy. And I use that company to publish textbooks and online courses, and of course, also to do game development. So that Battle Paddles game that I showed you the screenshot from, I am in the process of porting that over from XNA Game Studio to Unity. That is about 60,000 lines of code, so it's going to take a little while to port, but at some point that will be on the Burning Teddy website, burningteddy.com. And I'm also working on another smaller casual game that is called Balloons Extreme, and I'll actually post my progress on burningteddy.com as I build that game in Unity. So Burning Teddy, all the game development I'm doing is actually in Unity. So when I'm not teaching and I'm not doing game development, what am I doing? Well, a number of different things. But one of those things is cycling. So riding a bike is one of my joys in life, I guess. So these are my 3 bikes. The blue one is the oldest one, and that's really an old bike at this point. But I used it to really get into cycling, not racing so much, but doing long rides like a number of centuries, which are 100-mile bike rides, including at the time one of the 10 toughest centuries in the United States. And so that century had over 10,000 feet of climbing. That's what makes 100-mile bike ride harder than another is, elevation gain. And so I did a number of bike rides. The mountain bike, the one on the bottom, is a result of going mountain biking with some friends one day, and I loved it so much that I went out and bought the mountain bike the next day. The bike all the way on the right is my triathlon bike. So, being a cyclist, I did a lot of long rides. I also did a bunch of running, including a number of marathons and a running race that goes from the bottom to the top of Pikes Peak here in Colorado Springs. I did that running race multiple times. And once you've biked a long time and run a long time, you say, well, you might as well do some triathlons as well. Just add a swim and you'll be fine. And so I've done a variety of triathlons, all the way from sprint distance, which are really short, all the way up to an Ironman distance race. So I've done a range. Really, the other thing, other than, interesting, like, reading books and stuff like that, the other leisure thing I do is I play video games. That should come as no surprise to you. And so the question is, what kind of video games do I play? And you should pause the video, guess in your mind what those might be, and then you can move on to see a screenshot of what I use to play my video games. You can see, and as you can see, racing games are my passion. So really racing simulations, so, realistic racing games rather than arcadey racing games. And if you're interested in all the details of that racing rig, you can go to the PDF that I've provided as a resource for this lecture. So there you have it. None of this has anything to do with course content, but it gives you a little more insight into who's teaching you in the course. In this lesson, we'll learn about our first data structure, and that's kind of a lie because the arrays and lists we've looked at previously are also data structures. But we're going to build something called a dynamic array. And a dynamic array is an array that can grow in size as you need it to. And that's very much like a list in the system collections generic namespace, but we're going to build this one ourselves. And in the next module, we'll do something called algorithm analysis to quantify the performance of the operations in our dynamic arrays. So we'll learn how to implement dynamic arrays, including both unordered dynamic arrays, where we don't care about the order of the elements in those dynamic arrays, and ordered dynamic arrays. We'll start by doing that for integers, and then we will turn our dynamic array class into something called a generic. And doing generics is a very common thing because all of the collection classes in the system collections generics namespace are in fact generics. So that means we'll be able to store any data type we want in our dynamic array instead of ints. And then finally, because we actually need to do something called implement an interface to have an ordered generic dynamic array, we will learn how we can implement an interface. In this lecture, we'll learn how to implement an unordered dynamic array to hold ints. So that means that we will grow the array as we need to as we add elements to the array, but we don't care what order those elements appear in the array. We'll start by looking at the parent class for both the unordered and ordered int dynamic arrays. So this is an abstract class because there are some methods in here that we don't know how to implement. We'll leave that to our child classes. We have an expand multiply factor. So once the underlying array here gets full, we're going to need to expand it. And the way we'll expand it is we will double its size each time we need to expand it. And that has been shown historically to be a reasonable approach. We don't want to just add 1 to the array size every time, because then we'll end up having to expand it all the time. But we don't want to multiply it by 100 either, because we can end up wasting lots of memory that way. So doubling the size each time we need to expand it is reasonable. Speaking of that underlying array, here it is. So it's an integer array called items. And we're going to keep track of the count as well, because in this array, some of those items will be valid and some of those items won't be valid. And so we need a way to keep track of which ones are valid and which ones aren't, and count is the way we're going to do that. Here's our constructor. We create a new array with 4 elements, and we set count to 0 because at this point, the array is empty. The only property we provide for the array is count. And here are those methods that we don't know how to implement here in the parent class. So we've made all 3 of them abstract. So we're going to be able to add something to our int dynamic array. We're going to be able to remove something from our int dynamic array, and we'll be able to find the index of a particular item in our int dynamic array. And each of the child classes, both of the child classes, will implement those 3 methods in different ways. Clearing out the array is a very straightforward operation. All we have to do is set count to 0, which indicates that there are now no valid elements in the array. Of course, the elements in the array are holding whatever values they used to hold, but we don't care. There's always bits in elements of an array, and we're indicating that none of those values are valid at this point. The last public method we have in the parent class is the toString method that just converts the int dynamic array to a string of comma-separated values. We do have one protected method, and that protected method expands the array. So if in fact the array is full and we want to add an item to it, we need to make it bigger. Now we know that once we've created an array object, we can't actually increase the size of that array object. So here's what we do. We create a new array called new items, and we make the size of the new array the size of the current array multiplied by that multiply factor. So now we have new items, an array of twice as many elements as the current array of items. Now we copy everything from the items array into the new items array. And finally, we change items to refer to new items. So because arrays are reference types, we can just change the reference for our items array to be a reference to that new array that we created. And the old array will just get garbage collected whenever the garbage collector decides to collect the garbage. That's it for the parent class. Let's look at the child class for an unordered int dynamic array. As you can see, I've made it a child class of that parent class. I have a constructor that just calls the constructor for the parent class. And here are those abstract methods. So the first one is adding an item to the unordered int dynamic array. The first thing we have to check for is whether or not we need to expand the array. So if count, the number of valid values in the array, is equal to the size of the array, that means we don't have any room to add another item to the array, so we need to expand it, which is what we do here. Now that we've expanded the array, we add the item at items count, and we increment count. And you should go do an in-video quiz about this. Okay, so count keeps track of the index of the next place we're going to add an item. So if you think about this, if count is 4, then the indices for the valid elements in the array are 0, 1, 2, and 3. So items count is the next available slot for a valid item when we need to add one. It's also useful that count happens to be the number of elements in the array as well. So we're using count for double duty here, and that's really handy. The next method is to remove an element from the array. So the first thing we do is look for it. And we'll talk about the index of method soon, but if index of returns -1 for the item location, then the item we were looking for doesn't appear in the array, so we return false. Because we haven't removed it, it wasn't there in the first place. Otherwise, Item location is the location of the element that we're removing, so we can just copy the element at the very end of the valid elements in the array into that location instead, and then we decrement count and return true. The last method in the unordered int dynamic array class is index of, so we need to look for a particular item. This is pretty straightforward. Because this is an unordered int dynamic array, the only thing we can do is start at the beginning and look for the item we're looking for until we either find it or we get to the end. So this for loop walks that array, and if in fact the current element we're looking at is the item we're looking for, then we return I, the index of that element that we just found. And if we look through all of the valid elements in the array and we don't find the item, then we return -1 because we didn't find it in the array. So that is both the parent class, int dynamic array, and the child class, unordered int dynamic array, for an unordered array that can grow as we need it to. To recap, in this lecture we learned how we can implement a parent class for a dynamic array of ints, and we also saw how we could implement a child class for an unordered dynamic array. In this lecture, we'll see how we can implement an ordered dynamic array to hold ints. So the difference between this lecture and the previous lecture is this time we do care about the order of the elements in the dynamic array. Our ordered int dynamic array class keeps the values in the int dynamic array sorted in order from smallest to largest. So we start with the constructor that just calls the constructor in the parent class. This is of course also a child class of int dynamic array. And now we get to those three abstract methods that we need to implement. Add is of course different from the add for an unordered dynamic array, but we do still need to check to see if we need to expand the array. That's always our first step to make sure that we have enough room in the underlying array for the item we're about to add. This next piece actually finds where we should add the item. Because we're keeping this sorted, we need to make sure we put this new item in the correct place. So what we do is we start our add location at 0. So that means we're assuming we're going to add the new item at the very front of our array. But then we do this while loop to actually find out where we really ought to add it. So while add location is less than count, because we want to make sure we haven't gone past the end of the valid elements in the array, and while whatever is at add location is less than item, so we haven't found the place we should add yet, we increment add location. So when this while loop ends, add location is exactly the index at which we should add the new item. Now that we know where to add the new item, we call this helper method that we'll look at when we get to the end of this class. But basically this helper method shifts everything up from add location to the end of the valid elements in the array so that we can then insert the new item at add location. And of course, because we just added something to the array, we increment count. So obviously this is harder work than when we were adding an item to an unordered int dynamic array, because we have to do all the work to make sure that we find the right place and then move things around to make room for adding that new item in the right place. Removing is also harder. We still do the first part that we did before. We check to see if the item is in the int dynamic array, and if it isn't, we return false because there's nothing to remove. But we can't just copy the thing at the end of the array into the location that we want to remove, because that is likely to screw up the ordering in the array. So instead, what we need to do is we need to shift everything down And because we're starting here, we're actually going to shift item location +1 down onto item location. So writing over what's in item location, but we do that from item location +1 all the way to the end of the valid elements in the array. And then we decrement count because we just took something out of the array, and we return true because we successfully did that work. The index of method is more complicated than the others because this actually implements something called a binary search. So we'll actually talk about binary search in more detail when we do algorithm analysis in the next lesson. But the big idea here is that we pick the middle of the array and we check to see if that's the item. And if it is, we're all done. But if it's not, we know which side of the array to keep looking in because the array is ordered. So if item is less than the middle, it's got to appear in the left-hand side of the array if it appears in the array at all. And if item is greater than the middle, then it has to appear on the right-hand side of the array if it appears at all. And we actually just keep doing that until we either find the item or we run out of array to look at, in which case we're all done. So here is code that calculates the middle location and the middle value, the value at that middle location. And we check to see if that's the one we're looking for. And if it is, that's awesome. We found it. Otherwise, here's where we split the data set. So if the middle value is greater than item, that means that the item is on the left-hand side. So we shift the upper bound down. So the lower bound tells us the lowest index for the array or the subarray that we're looking at to try to find our item. And the upper bound gives us the upper index for that subarray. So if we keep shifting lower bound and upper bound, then we can sort of keep shrinking the subarray that we're looking at the correct location based on the item and the ordering in the array until we get down to one element or we find the item we're looking for. We also are checking here whether lower bound is greater than upper bound, but I will say that this code that I provided actually had an error in it. And so this is the buggy code, just so you can see the error, and then there's correct code here. And I address this in more detail in the dynamic arrays reading. So you should go sort of read through what happened with the bug and why I changed it this way and so on. We will actually see when we get to module 3 of the course another way to do binary search, and it's called recursion, and we'll just wait until we get there, but it's actually a pretty powerful way to approach this problem and lots of other problems, and that actually might seem more clear to you what's going on. But if you don't really understand what's going on here, make up an array with pencil and paper and go look for an item in it and walk your way through the code, and you'll see that this actually does a binary search to try to find the item. And we can only do a binary search because the array is ordered. I mentioned the shift up and shift down helper methods, and here they are. So shift up, we pass in the index, and what we do is we run I from count down to the index just above where we want to start shifting, and we decrement I. So we're starting at the right-hand side, and we keep setting whatever is at I to whatever is the element just before that element. So we're copying everything up here, starting at index. Similarly, shift down does something much like shift up, except we start at index. This one actually goes from left to right. We start at index, and as long as we're less than count, we increment I, and we copy the element at index I into the element at index I minus 1. So you should be able to see how this is copying everything down one space. And that's it for our ordered int dynamic array. As you can tell, the code that we write to keep our int dynamic array ordered is more complicated than when we didn't care about the ordering of the elements in the array. To recap, in this lecture, we saw how we can implement an ordered dynamic array class to hold ints. In this lecture, we'll see how we can make our dynamic array class a generic, so it can store any data type, not just ints. And this is really common practice. That's why all the data types in the system collections generic namespace are generics. The way we actually make our dynamic array generic is we add this notation after the class name. And this looks a lot like the notation you see when you create a list object to hold a particular type, because lists are generics as well. And we provide the type we want them to hold between the less than and the greater than. Here in the class definition, we actually put the same sort of notation, but this T stands for the type that we're going to add. The next change we make is here, where we declare an array of type T rather than type int. Then in the constructor, we create a new array of whatever type T is. Count stays the same. Our abstract methods all take in a T parameter rather than an int parameter. Clear works the same, and toString works the same. So we only need to make minor changes to our parent class to support making it a generic rather than just making it store ints. We make our unordered dynamic array a generic by using that same notation here, and it is still a child class of that parent class. Notice we put that notation at the end here as well. The constructor doesn't change at all. As I mentioned, add now takes a parameter of type T, but none of the rest of the code changes because it all works the same way. It's just adding an item of type T rather than an item of type int. Similarly, the remove method takes a parameter of type T and the rest of the code is identical. And index of has one other change. We include a parameter of type T, but you'll also notice that here, instead of using equal, I'm actually calling the equals method. So as long as the type T, that is the element type for everything we're storing in our dynamic array, implements the equals method, this comparison will work just fine to find the item when we're looking for it. Our ordered dynamic array actually has something new here at the end. So we're providing a constraint for the type that we can include in an ordered dynamic array. And we're actually saying that whatever type we want to put into this ordered dynamic array has to implement the comparable interface. And we're actually going to look at how we implement an interface in the next lecture. But the bottom line is the comparable interface says that the T type has to implement a Compareto method, and we need that Compareto method because we need to be able to compare two of the elements to decide the appropriate ordering in this ordered dynamic array. The constructor stays the same. T type for the parameter, and a change here. So instead of just comparing one element to another using less than, we use the Compareto method. And the way the Compareto method works is if this item is less than this item, then Compareto, by definition, returns a negative number. So this Boolean expression here is basically checking if the item at add location is in fact less than item, which is just what we were doing before. Remove works the same way it did before, except with T there. And index of works the same way as it did before, except that we use Compareto to see if we found a match, and we also use Compareto to decide which side of the subarray we should search next for the item. And the shift up and the shift down methods work the same way they did before with no changes. To recap, in this lecture, we learned how we can make a class a generic, and we also learned how we can add a constraint if we need a data type to implement a particular interface. In the previous lecture, we saw how we can add a constraint to a generic if we need a data type to implement a specific interface. In this lecture, we'll learn how to implement an interface. In this example, we want to create an ordered dynamic array of rectangles, and then add rectangles to that array, and then print the rectangles in the array. So here's our rectangle class at this point. We just have width and height fields, a constructor, properties to get at the width and height, and a toString method so we can convert the rectangle to a string to print it out in our main method. So the first thing I want to do is create an ordered dynamic array of rectangle. And I'll just call it rectangles. And of course I'll create a new one. And I'll hit enter so you can see it all on the screen. So when I compile, I get an error. And the error says that the rectangle class doesn't implement the iComparable interface. And we know that because we didn't do anything to implement that interface. So over here in the rectangle class, the first thing we do is we say that this class will implement the iComparable interface. And you'll notice that the syntax here is just like when we say a particular class is a child class of another class. But in this case, we're just saying we will provide whatever methods the iComparable interface requires. And if you remember from our discussion about the ordered dynamic array, the method that we need is the Compareto method. If I try to compile again, I get another error, and this error says that the rectangle class doesn't implement the Compareto method. So once I say I'm going to implement a particular interface, I'm required to provide all the methods in that interface. How do you know what those methods are? Well, you read the documentation. Here's the documentation for the iComparable interface, and you'll notice that it says that it defines a type-specific comparison that the class implements to order or sort its instances. And that's exactly what we need, right? And if we scroll down, we find out there's a specific method, and that's all we need. And if we click on that method, we can get more details about how that method is supposed to work. Specifically, the Compareto method compares this object to another object of the same type and returns information about the relative order. So if the current instance is before the parameter, then we return a negative number. And if they're at the same position in terms of order, then we return 0. And if it's after the parameter, then we return some number greater than 0. If in fact the parameter is not the same data type as the class in which we're implementing this method, we actually throw an argument exception. And there is an example right here, and the easiest thing to do is just to copy this and bring it over into our rectangle code, and then make the appropriate adjustments. So first of all, I'll add a documentation comment. And it returns relative order. And this is the object to compare to. I'll do some adjusting of curly braces and add some comments as well. So this is always greater than null, and that's by definition in the documentation. You are allowed to omit the curly braces for an if statement if you only have one statement, but I always include curly braces, so I'll do that now. We'll also make sure that the object is actually a rectangle. So I'll say check object type. And of course, this is a rectangle. And remember, this is like a typecast. So if we say obj as rectangle, if this is successful, if in fact obj is a rectangle, then we can now treat, I'll rename this to be other rectangle instead. So if this is successful because obj is a rectangle, then we can now treat other rectangle as a rectangle object. If obj is not a rectangle, then this will be null at this point. And that's why we have this check for null. And if the object is not a rectangle, so obj isn't a rectangle, then we throw the exception because that's what the documentation tells us we should do. If in fact we actually have a rectangle here, we now need to decide how do we tell which one comes before the other in the sort order. And I'm going to say that we're going to sort by area. So if width times height, so this is the width and height of the rectangle we're inside right now. If that is less than the other rectangle width times the other rectangle height, then that means that this rectangle comes before the other one in the sort order. So I'll return -1. Remember, it just has to be any number less than 0, but I typically return -1, 0, and 1 from my Compareto methods. We now need to check to see if they're equal. So if they're equal, I will return 0. And the only other possibility is that the current rectangle we're inside comes after the other one, and I don't have to check anything at this point. I can just return 1. So we knew when we implemented the iComparable interface that we had to provide a Compareto method, and we read the documentation for the Compareto method to see exactly how that method had to behave. I can now compile just fine. So this is very exciting. We've finally been able to create the array of rectangles. The big idea, right, is that we actually learned how to implement the interface that we needed to implement in order to create an ordered dynamic array of rectangle objects. The rest of this is pretty straightforward. So we will add a few new rectangles. Let's add a 3x4 rectangle. A 2x2 rectangle. And a 1x2 rectangle. Finally, we'll print out the rectangles in the array to make sure that they ended up in the array in sorted order the way we expected them to. So I will just console write line the rectangles to string. And if I control F5 at this point, we see that we get the smallest area rectangle first, and then the middle area rectangle next, and then finally the largest area rectangle. So the ordered dynamic array worked properly given the fact that we implemented the Compareto method in the rectangle class the way we had to do based on the iComparable interface. To recap, in this lecture we learned how to implement an interface, and we also learned that we need to read the interface documentation to make sure we implement that interface properly. This lesson is all about algorithm analysis. So what will you learn in this lesson? You'll learn what algorithm analysis is, you'll learn why we do it, or in other words, who cares, and you'll learn how to do it, because learning that it's really important isn't good enough, you actually need to understand how you can do it. So what is algorithm analysis anyway? Well, it's analyzing an algorithm to determine how long it will run, which is the most common, or how much memory it will take, which we sometimes are concerned with, in the worst case. So you should start with an in-video quiz about algorithms, and now you should move to an in-video quiz about the worst case. So we worry about the worst case because it can't get any worse than that, right? So we have to do our analysis in the worst case, because if we're over-optimistic and somebody bases decisions on our analysis, then they could experience bad performance that they didn't expect because we were overly optimistic with our analysis. And that's really the point of why we care. So we care about algorithm analysis because it helps us make decisions. It helps us decide what data types we want to use for the particular problem we're going to solve, because some data types are better than others in terms of the operations and the time it takes to do those operations. For one example, adding an element to a list can sometimes take constant time and sometimes can take a long time dependent on how many items are in the list. And we'll look at that in more detail when we analyze our dynamic arrays. Adding to a linked list, which we'll actually get to next week, is always constant time. So if we're planning to do a lot of adding to our data structure, we would use the algorithm analysis results to say, oh, a linked list is actually better than a list for that particular problem. We also can use our algorithm analysis results when we're deciding which algorithm to do. And that is most commonly in play when we're talking about doing things like sorting something. There are lots of sort algorithms, and they have different algorithmic complexities, amount of time it takes for them to run. And so you would generally pick a better one compared to a worse one. And that's, again, a result of algorithmic complexity. So to recap, in this lecture, we learned what algorithm analysis is, and we learned why we care. In the previous lecture, we learned what algorithm analysis is and why we care. In this lecture, we'll learn about something called Big O notation. So what problem are we trying to solve? The problem is that we want to understand the complexity, how long it takes, or how much memory it takes for a particular algorithm to execute. And what do we do about that? Well, we do algorithm analysis, but at this point, all we know is we could say, wow, it's really fast, or gee, it's really slow. And that's not precise enough for a science like computer science. So what we need to do is we need to figure out a way, how do we specify what we mean by the complexity of a particular algorithm? And what we do is we find a function that will serve as the upper bound for the performance of a particular algorithm. So this is regularly in terms of something like the number of things in a list, which we call n. So we try to figure out a function in terms of n, that will always be above how long it takes for our particular algorithm to run. And as I mentioned in the previous lecture, and as you see above, sometimes we evaluate memory, but regularly we're talking about time. So now we know we need a function that serves as the upper bound, and there ought to be a notation we can use to specify that function. And of course there is, and that notation is called Big O notation. So you should go do an in-video quiz about Big O, and now we should go look at a picture. So here's a number of functions that could represent the upper bound on the time it takes a particular algorithm to run. The horizontal axis is n, where n is the number of data points we're trying to process with our algorithm. And the vertical axis is time. So this certainly could be space if we were doing algorithm analysis for space requirements. But let's just focus on time until I mention we might want to do otherwise. So as you can see, the order 1, we're using Big O notation. So order 1 means constant time, a constant time algorithm. So there's a line there that is just set at 3 for time. I didn't put any markings on the vertical axis, but I'll tell you, I know that that is a constant of 3. 3 clock cycles, 3 seconds, 3 whatever, it doesn't matter. Something might only take a particular amount of time, no matter how large the data set is. We also have order log n, and that is log base 2 of n, not log base 10 of n or natural log or anything like that. It's log base 2 of n, so that's the green line. And then we have the line marked order n, so that's a linear function. Then we have the order n log n teal colored line on toward the left, and that is called log linear. And then finally we have a quadratic function, that black curve that climbs pretty steeply there, that says order n squared. So really what we're going to figure out with some approximation, because we're going to ignore lots of details and only really pay attention to the contribution of n to the complexity of our algorithm, but we will figure out whether the particular algorithm we're looking at always falls below that order n line, for example. And if it does, then it's an order n algorithm, unless it's an order log n algorithm. So we find the sort of tightest bound using 1 log n, n log n, or n squared to figure out how complex our algorithm is. Don't worry, we'll do some examples. Before we end this lecture, you should do one more in-video quiz. And to recap, in this lecture, we learned about Big O notation. In the last couple of lectures, we've been talking about algorithm analysis and Big O notation, and that probably still feels pretty abstract to you. So in this lecture, we'll actually go through some concrete examples. Before we do, you should take an in-video quiz. Okay, the big idea here with our algorithm analysis is, let's say we actually came up with a math equation, a function, for how long our particular algorithm would take to execute, like the example I gave you. The first thing we do is we throw away all the numbers. All we keep are n, any term that has an n in it. Once we do that, we can just pick the highest order n term, the term that will dominate the rest. So n squared grows much faster than n log n, which grows faster than n, so we can throw everything away except for the n squared in the example. So that example was order n squared. Okay, so some examples. We'll start at the lowest cost or fastest complexity, and that's constant time. That's order 1 is the way we specify it takes constant time. Now, that doesn't mean no time. It doesn't mean instantaneous. It just means that the time it takes to do it has no dependence whatsoever on n. So one good example of this is accessing a specific element in an array. So it doesn't matter if our array has one thing in it or 20,000 things in it, accessing a particular element takes constant time, because what we do is we take the index, we multiply it by how large each element is, and then we add it to the base address of the array. So it doesn't matter how big the array is. We do a multiplication, we do an addition, and there we are with the address of the element we're trying to access. So that's a constant time operation where the time it takes to do that operation is not dependent on n. The next one up, and there are actually some sort of more obscure complexities in between the ones we're talking about, but I'm talking about the most common ones. The next one up is order log n, and that's called logarithmic. And this log, by the way, is log base 2. It's not log base 10 or natural log or anything like that. It's log base 2. And a good example of that is binary search. And let's walk through a binary search example so you can see why it's order log n. Here's our binary search example. We're going to look for the number 3 in this list of numbers that's right next to it. And there are 11 items in that list. We'll come back to that comment in a few minutes. So what we do is we check the middle of the list. Now it's important to note that this list has to be sorted in either ascending or descending order. We can do a binary search on either sorting order, but most people will sort lists in ascending order, so that's how we did it here. So we check the middle of the list, and it's 21, and 3 is less than 21. Now because the list is sorted, we know that if 3 appears in the list, then it's going to be the left of 21. And so we split the list in half, and we now look for 3 in that list 1, 3, 5, 12, 17. We check the middle of that list, and that's 5, and we know 3 is less than 5, so we look for 3 in 1 and 3. Now we check the middle of the list, and you may well say, well, there is no middle, there's only 2 values, and so we have to consistently decide as we run our binary search algorithm to either round down or round up. I'm going to round down because when we implement this, that's how it will work. And so now we're going to compare 3 to 1, and 3 is greater than 1. So we're going to look for 3 in the list of one element, 3, and we found it. And of course, if that number had been 4, we wouldn't have found it, but we would have been done anyway because we got down to a list of 1, and that list of 1 wasn't 3. But in this case, we found it, and that's great. Because we split the list in half every single time, this is an order log n algorithm. Log base 2, not log base 10 or natural log or anything like that. But we only have to do, for this list of 11 items, log base 2 is slightly higher than 3, but we'll have to say 4. And it turns out that we did 4 comparisons here. We checked against 21 and 5 and 1 and 3. And so, as you can see, the number of comparisons that we need to do when we do a binary search is order log n. Now, it's important to note that because each comparison takes a certain amount of time, and because, depending on how the rounding works, we might end up doing one additional comparison, the actual equation for this might be something like 3 log n plus 3. And the important things to know are, we don't care about constants, because if we can have an upper bound on top of our function that's 20 log n, then we don't care that we had 3 log n plus 3. It's order log n. So the great thing about algorithm analysis is any number, any actual number we end up with, we can just throw away when we're converting to big O notation. So this is an order log n algorithm, even though if we were precisely trying to calculate how many clock cycles it would take, it might be 3 log n plus 3, for example. But we don't care because we throw away the numbers. Okay, we have 3 more examples to at least briefly discuss. The next one is order n. So this is linear in n. And the best example of this is doing a linear search. Let's say you were looking for a particular card in a deck of cards, and you didn't have the cards in any sort of order. So to look for a particular card, you have to look at the first one, and if it's not the card, look at the second one, and if it's not the card, look at the third one, and so on. And in the worst case, remember we're doing worst case analysis here. In the worst case, we might find the card we're looking for at the very end of the deck, or we might not find it at all. And in both of those cases, we had to look at n cards, where n is defined as the number of the cards in the deck we're searching, to do our linear search. So linear search is an order n operation. The next one is something called log linear. It's order n log n, and we see this most commonly in various sorting algorithms. So there's something called merge sort, and there are many sorting algorithms that are n log n, but merge sort is one such algorithm that actually takes n times log n time to do. Now, the interesting thing about it is that we already saw log n with binary search, and we saw that it was log n because we split something in half each time. The way merge sort works is we split something in half each time, and that's where the log n comes from. But then we have to actually merge these sublists that have been sorted back together, and at the end, that merge actually takes n time. So that's why we get n log n. Finally, quadratic means order n squared. And we see order n squared in lots of sort of basic sorting algorithms like bubble sort and insertion sort and selection sort. And we're actually not covering sorting algorithms in this class, but you will probably come across sorting algorithms somewhere in your game programming career. So these last three are the highest we'll go with the sort of practical things that we'll do in programming. There are other algorithms that are even worse, so we won't worry about those, thank goodness. Okay, you should do an in-video quiz, and the answer is the number of loop iterations. That tends to be the key thing in our algorithm analysis, and we'll see that a lot as we actually continue with our algorithm analysis work. To recap, in this lecture, we saw some algorithm analysis examples that actually used big O notation. From this point forward, we'll do our algorithm analysis on C# source code, because C# is just a language that we use to express our algorithms. Those step-by-step plans for solving a problem are the code we write. And so we'll do our analysis based on the actual source code that implements the algorithms that we want to analyze. In this lecture, we'll do algorithm analysis on our dynamic array and unordered dynamic array classes. We'll start by doing the algorithm analysis for our parent class because that applies to both the unordered and the ordered dynamic arrays. So let's take a look at clear. What is the algorithmic complexity of clear? Well, the only thing it's doing is an assignment, and assignments take constant time. Now remember, constant time doesn't mean zero time. It just means that the amount of time it takes has nothing to do with how many elements are currently in the array. So because we only do one thing that takes constant time, this is order 1. When we do the toString method, we see that we do a for loop over each of the elements in the array. And that means that this for loop executes n times, where n is defined as the number of valid elements in the array. We still need to look inside the loop to make sure there's nothing else that we need to worry about, but append is order 1. And checking a Boolean expression is order 1, and append is order 1. So the entire body of the loop is order 1, or constant time, not zero time, but constant time. So all we care about is this loop that goes n times, and the last line of code converting to the string is also constant time. So the only thing that's dependent on how many valid elements there are in the array is this for loop that executes n times, so the toString operation is order n. Expanding the array is also order n. This is constant time, this is constant time, and this is constant time. But this loop executes n times because we have to copy each of the valid elements from the old array into the new array. So because we have this for loop that executes n times, the expand operation is also order n. In the unordered dynamic array class, adding is an interesting operation. Here's the problem. Evaluating this Boolean expression is constant time. Doing this assignment is constant time. And doing this increment is constant time. But expand, as we just discovered, is order n. So if we don't have to expand, if this Boolean expression evaluates to false, then this is order 1. But if we do have to expand, this is order n. So really, in the worst case, right, the worst case is that we're expanding the dynamic array, so that makes it order n. However, it is very common because as the array gets larger, we need to expand it less often. That's why we're doubling it each time. It turns out that most of the time, this is order 1, except in those cases where we need to expand it, and then it's order n. So worst case is order n, but if you get a chance to describe it a little more, you can say it's order 1 if you don't need to expand the array, and it's order n if you do. There's actually a term in algorithm analysis that lets us say that the add operation is order 1 amortized. And this comes from finance, of course, where we amortize investments over time. So most of the time this is order 1, and then in rare cases it's order n. So there are a variety of ways to address this, but this is a tricky one because the algorithmic complexity of the add operation depends on whether or not we need to expand the array. Luckily, we don't have that problem here in remove, because we'll evaluate index of. I guess we better go evaluate index of now. Index of does a for loop over each of the elements in the array. So in the worst case, we have to look at every single element, and either we find the item we're looking for at the very last location in the array, or we don't find it at all and we come down here. But again, this for loop goes n times. This is constant time, and this is constant time. So the body of the loop is constant time, but the outer loop goes n times. So index of is an order n operation. That means that this line in the remove method is order n. This is constant time. This is constant time. These are each constant time, but this order n call to the index of method at the beginning of the remove method makes remove an order n operation. To recap, in this lecture we got practice doing detailed algorithm analysis on C# source code. In this lecture, we'll do algorithm analysis of our ordered dynamic array class. Remember, the ordered dynamic array is a child class of dynamic array, so we don't have to do our algorithm analysis again on those operations that are contained in the parent class. We do need to do an analysis of the operations included here, so we'll start with add. again, we have that expand that's order n. So we may end up with order n, but remember, it could always be worse also. So we have to check for worse. And we take a look at this while loop, and we determine how many times this while loop will execute in the worst case. And in the worst case, we need to add the item at the very end of all the valid elements in the array. So this while loop could, in the worst case, execute n times. And incrementing add location is a constant time operation, but that means that the while loop is order n as well. We also need to consider what shift up could be. And shift up could be order n in the worst case, but that's only if we actually need to insert the new item at the beginning of the array. So the worst case here is exactly the opposite of the worst case here, because if we're adding the new item at the beginning, then this while loop doesn't execute at all. So the combination of these two things is actually order n. And this is constant time, and this is constant time. So basically what we have is order n plus order n plus some constant time stuff. And that means that this would essentially be 2n, but remember, we throw away the numbers when we're talking about algorithmic complexity. So adding is actually order n. Removing, we need to go look at index of and figure out its algorithmic complexity. This is kind of tricky to do. So the big idea is that we are chopping the array in half each time we're looking for the item. So in the worst case, this while loop executes log base 2 of n times. And everything inside here is constant time. So that means that this chunk, the while loop and the loop body, executes log base 2 of n. And remember, we regularly just say log n when we're talking about algorithmic complexity. So this is log n. That means the index of operation is order log n. Coming back up to remove, we now have an order log n operation. This is constant time, this is constant time, these are constant time, but we have the shift down operation here, and we need to go evaluate the algorithmic complexity of shift down. So we need to consider the worst case here. What's the worst case for shifting things down? The worst case is, in fact, if index is 1, which means that we're going to shift everything down. We're removing the very front element in the array. So we have to shift n-1 things down. And that means that this for loop executes n-1 times, which is order n. So the shift down operation in the worst case is order n. So back up here and remove, this contributes order n to the complexity. So we have an order log n added to constant time, order n, constant time, and constant time. So essentially we have order log n plus order n, but we can get rid of the order log n term because as n gets large, the order n term dominates the order log n term. So we always take the highest order term in our algorithmic complexity, and that means that the remove operation is order n. Before we finish this lecture, you should do an in-video quiz, and the answer is sometimes the ordered dynamic array operation is faster, like index of is log n for the ordered dynamic array because we can do a binary search, versus order n for index of the unordered dynamic array because we have to do a linear search. Sometimes it's the same because remove was order n for both, and sometimes it's actually worse. And so when we add to an ordered dynamic array, that's order n, And when we add to an unordered dynamic array, while we do know it's order n in the worst case when we have to expand the array, it is commonly constant time, order 1, instead. To recap, in this lecture, we got more practice doing detailed algorithm analysis on C# source code. Welcome to the linked list lesson. What will you learn in this lesson? You'll learn what a linked list is, and let's take a look at a picture of one now. So a linked list is comprised of a set of linked list nodes. Each of those rectangles in this picture is a node, and each node holds a value, those numbers that we see, and a reference to the next node in the list. So that's the linking of the list. That's how nodes are connected together, is by these links between the nodes. And this is a picture of a singly linked list. There are certainly doubly linked lists where each node also points to the previous node in the list as well. We also maintain a reference to the head or the front of the list so that people can actually access the different nodes in the list by starting at the head and following those next links to move along the list from node to node. We'll also learn how to implement a linked list, and finally, we'll do algorithm analysis of the linked list implementation that we create. In this lecture, we'll implement a linked list. In practice, you should just use the linked list that's available in the System Collections generic namespace, but implementing our own linked list gives us additional practice both in our programming and in our algorithm analysis. We'll start by looking at each node in the linked list, which I've called linked list node, and our linked list node is a generic so we can store any data type we want. There are two fields. We have a value that we're storing in our linked list node, and we're storing a reference to the next node in the linked list. So we're implementing something called a singly linked list here, where each node only points to the next node in the list. There's also something called a doubly linked list, which you'll get to implement if you do the exercise that doubles the links. And in that particular implementation, each linked list node has a reference to the next node in the list and a reference to the previous node in the list. And it turns out that having that link back to the previous node is particularly helpful if you need to traverse the list from the tail, the end of the list, to the head. We have a constructor that simply sets the value of the node and next to whatever node is passed in. And of course, we have properties that access the value, so we can only get the value of the linked list node, but the next property lets us both get the next property, which we need to be able to do if we ever want to walk the list or traverse the list from the beginning to the end. And we also provide the set accessor for this property because we may need that. We will need that if we are going to add and remove nodes from the list, which of course we need to do for it to be a useful data structure. So this is one of the building blocks of a linked list. Each node is a piece of the linked list, and then we just hook them all together to form our linked list. Speaking of our linked list, here's the class for that. It is an abstract class because the add method is abstract, but really this linked list parent class for the sorted and unsorted linked lists contains most of the functionality for the linked list. We have the head, the front of, if you want to think of it that way, but it's regularly called the head of the linked list, and that's a reference to a particular node, the node at the very front of the linked list. And for convenience, we'll keep track of the count of the number of nodes in the linked list. We could, in fact, walk the list every time somebody wanted to know the count, but this is a quicker and more convenient way to actually keep track of the count. The constructor sets head to null and count to 0 because when we construct a linked list, it starts as empty. We have the count property that returns how many nodes are in the list. And we have the head property that returns the head of the list. So anyone who actually wants to use our linked list will start at the head and walk along processing the different nodes in the list. Here's that abstract add method because an unsorted list can do this much more easily than a sorted list can. Clearing is more complicated than we saw with the dynamic arrays. So here's the issue. We have references to all the linked list nodes in our linked list, and the way garbage collection works is if an object in memory has a reference to it, that means it can't be garbage collected. So we can't just set the head to null and set the count to 0 because all those nodes that are hooked together in our linked list will have references to them, and so they can't be garbage collected. So as long as we have something, at least one node in our linked list, we will release or disconnect all those nodes. And we'll see this pattern again and again for how we actually walk a list. So we'll set previous node to head and current node to head.next. So now we're holding the first two nodes in the list. And if this list has only one node, then current node is null at this point. This is not a standard piece of how we traverse a linked list. So at this point, we are disconnecting previous node from current node. And while the current node isn't null, and so current node will be null when we get to the end of the list, we make previous node current node, so we jump one node forward with previous node. We set current node to current node.next, so we jump current node one node forward. And then we disconnect current node from previous node. And this is the way we disconnect all those references for the nodes in our linked list. And once we've done that, we set head to null and count to 0, just like we did in the constructor, to indicate that we now have an empty linked list. To remove something from the list, first thing we check is the list empty? Because we can't remove anything from an empty list, so we return false in that case. The next thing we check is to see if we're removing the head of the list. Because remember, for consumers of this class, the head is kind of the only way that they can get at the other nodes in the list. They start at the head and they walk along the list. So if we remove the head, we need to make sure that the linked list still has a head. And the way we do that is we set head equal to head.next. So we're removing this node head, but before we do, we'll grab the next node that the head currently references and set head to that instead. And we reduce count by 1 as well. And of course, if this was a linked list of only one linked list node, setting head to head next makes head null, and reducing count from 1 to 0 is essentially saying now we have an empty list. Okay, so you'll find as you deal with linked lists that you have to check for special cases all the time. So this was checking for a special case and this was checking for a special case. Now we can go to the normal traversal. And this is really the normal pattern for traversing a singly linked list. So previous node gets set to head, current node gets set to head.next. And we'll see why we actually need this previous node later. And the reason is when we get to current node, if we haven't saved the previous node in a singly linked list, we can't find the predecessor of the current node. So we have to keep track of both in a singly linked list. Okay, while the current node isn't null, and while we haven't found the item we're looking for, we advance along the list. We jump previous node to current node, and we jump current node to current node.next. So this moves both of those things forward one node. When we're done, we either found what we were looking for, and it's in current node, or we exhausted the list, and current node is null. So we have to check this. And if current node is null, it means we didn't find it, so we return false. Otherwise, here is where we're actually removing that node. The way this linkage works is before we execute this line of code, previous node.next is current node. And if we set previous node.next to current node.next, we've just made that reference jump over current node, which means current node no longer has a reference to it. It's not part of the list anymore. And of course, we decrement count. So if this piece doesn't seem clear to you, you should actually write down an example on a piece of paper and see how this actually does remove that node. So you might wonder why the remove method is here in the parent class, because in our dynamic array, remove was in the unordered dynamic array and the ordered dynamic array classes because they worked differently. And they worked differently because removing from an unordered dynamic array, we just copied over the place where we wanted to remove, but removing from an ordered dynamic array, we had to shift things around. Remove works exactly the same for both unsorted linked lists and sorted linked lists. We have to find the node to remove, and then removing it works exactly the same way whether the list is sorted or not. Similarly, find is also here in the parent class. Remember, in the unordered dynamic array, we had to do a linear search for the item we were looking for, but in the ordered dynamic array, we could do a binary search, which was order log n instead of order n. We could only do that because arrays are something called a random access data structure, right? We can get at a particular element in the array with an index directly. A linked list doesn't work that way. We start at the beginning, at the head, and we work our way forward. So there's no way to do a binary search on a linked list. So find also is here in the parent class. This time we don't need to keep a reference to the previous node because we're not going to unlink anything. We're just looking for the current node. So we can start the current node at the head, and while it's not null, and while we haven't found the item we're looking for yet, we just jump current node to the next node until we either exhaust the list or find the item we're looking for. If we haven't exhausted the list, that means we found the item, so we return that node. Otherwise, we return null because we couldn't find that item in the list. This toString method simply starts at the head of the list, making sure we haven't reached the end, and while we haven't, we add the value to the string and then bump current node along to the next node, and we just walk along from the head to the tail or the end of the list, adding information to this string that we then return. That's it for the parent class. Luckily, the child classes are pretty simple because they only implement a constructor in the add method. The constructor just calls the base constructor. The add method for an unsorted linked list. If we're adding to an empty list, then we just make the head be a brand new node with the value we wanted to add and null for the reference to the next node in the list. Because there is no next node in the list, we're adding to an empty list. Otherwise, we can simply add to the front of the list, and the way we do that is we say that the head is a new linked list node with the value we're trying to add, and the next node is the existing head. So remember, what happens is the right-hand side of this assignment gets evaluated before we assign it to the left-hand side. So this is the old head that is now going to be referenced as the second node in the list by the new head once we do that assignment. And of course, we increment count because we just added something to the list. The sorted linked list again requires whatever type we're using as values in our linked list, implement the iComparable interface so that we can make sure we keep the order correct. We have our constructor. We have our add method. Again, adding to an empty list, same as before. If we're adding before the front of the list because the head value is greater than the item we're adding, then we do this, which is just what we did with the unsorted linked list. But usually in a sorted linked list, we actually have to find out where to place the node, and that's what this code does. So again, standard previous node, current node. While we haven't reached the end of the list and we still haven't found the right place, then we bump previous node and current node forward one node each, and then we link in the new node between the previous node and the current node because that's the place we wanted to put it. So previous node now refers to, as the next node in the list, the new one that holds the item, and that new node we're creating now references the current node as its next node. So we're basically inserting this node with the value we wanted to insert between previous node and current node, which is exactly what we need to do to keep this linked list sorted. And we increment count because we just added an item to the list. In this lecture, we learned how to implement linked lists and linked list nodes. We learned how to walk a linked list from the head to the end, often called the tail of the linked list. We learned about the difference between linked lists and random access structures. And we saw how we could support garbage collection when we cleared our linked list. In this lecture, we'll complete the algorithm analysis on the operations, our methods, in our linked list and linked list node classes. We'll start by evaluating the complexity of the clear method in the linked list parent class. And remember that this piece right here walks the entire list, touching each node to disconnect that node from the next node in the linked list. And that means that this while loop right here executes n times, where n is the number of nodes in the linked list. The rest of these lines of code are constant time, order 1 operations, but this while loop makes the clear operation an order n operation. To remove an item from the linked list, this is constant time, this is constant time, this is constant time, these are constant time. So here we walk the list looking for the node that we want to remove. And because the node might be at the very end, or the node might not be in the list at all, this while loop executes in the worst case n times. And that means that this chunk of code is order n. The rest of this stuff is constant time. So this while loop makes the remove operation order n. To find a particular node in the list, again, we have a while loop that walks the list, and again, the worst case is the node is at the very end of the list or not in the list at all, in which case this while loop executes n times. So this operation, because everything else is order 1, this operation is also order n. Finally, converting the list to a string, as you might expect, this part where we keep walking the list until we reach the end means that we touch every node to append its value to the string, and that means that this is also an order n operation. The only other thing to look at is the add method in the unsorted linked list and in the sorted linked list. Adding an item to an unsorted linked list, this is constant time, this is constant time, this is constant time, and this is constant time. So the add operation is an order 1 operation. And this is better than adding to a dynamic array, remember, because when we needed to expand the dynamic array, we needed to pay the cost of expanding the array and copying each element over. So add was sometimes an order n operation, even for an unordered dynamic array. And For our unsorted linked list, adding is always constant time. That is not true for the sorted linked list. We check for the empty list, constant time, constant time, constant time, constant time. Here's the piece that is not constant time. We have to iterate over the list, looking for the appropriate place to add our new node. And in the worst case, our new node needs to go at the very end of the list, and that means that this while loop executes n times as we walk the list looking for where we should put the new item. So because everything else is order 1, the add operation for a sorted linked list is an order n operation. To recap, in this lecture we got more practice doing algorithm analysis, and we saw again how the number of loop iterations has a major impact on the complexity of our algorithms. What will you learn about in the graphs lesson? You'll learn about what a graph is, so let's go take a look at a picture. A graph is a set of nodes, though when we talk about graphs, we regularly talk about each of these nodes as a vertex. So the plural of vertex is vertices. So we have a set of vertices, and those vertices are connected with edges. This is something called an undirected graph, because for each of the edges, we can follow that edge in either direction. So the edge between nodes 4 and 42, we can follow from node 4 to node 42, or from node 42 to node 4. In a directed graph, edges actually have a direction. So if we had an edge between 4 and 42, that edge could only be followed from 4 to 42, or from 42 to 4, depending on where the head and the tail of that edge was. This is also an unweighted graph, where the cost of following each edge in the graph is identical to the cost of following every other edge in the graph. We will often find it's useful to have a weighted graph instead, where each edge has a particular cost. It's pretty common to make the cost be the distance between those 2 points in the game world. If we're implementing a pathfinding algorithm to navigate through the game world, and in fact, we might even add something to the cost of edges that traverse harsher terrain, for example, if you have to go up steep slopes or cross rivers or those kinds of things. So we'll also find it useful to have weighted graphs where the edges have costs associated with them, but that's not the kind of graph that we're looking at here. We'll learn how to implement a graph, and we'll evaluate the algorithmic complexity of the operations in our graph. We'll then revisit dictionaries, which we looked at briefly in the previous course, but we'll look at them in more detail here so that we can use them to search a graph, because we regularly are looking for a path from a start node to an end node in our graph, and that's not surprisingly called pathfinding, and dictionaries will help us do that. In this lecture, we'll implement a graph, and C# does not provide a graph class to you, so if you need a graph, you need to implement one yourself. We'll start by looking at the class for a graph node. Lots of people call these vertices, or the singular would be vertex, a vertex in the graph, but I'm going to pretty consistently use the terminology node in the graph. It's a generic, so we can store any data type in the graph nodes, and it has 2 fields. It has a value, and it has a list of the other graph nodes that are neighbors of this graph node. So that means that this graph node is connected to its neighbors with edges. The constructor simply sets the value of the node and creates an empty list of neighbors because a new graph node doesn't have any edges connecting it to anything else yet. We can get the value of the node and we can get the list of neighbors, but here's something new. We don't actually just want to return the list of neighbors to somebody because they could then modify the contents of that list by adding and removing elements from the list, and that would change the neighbors for this particular graph node. If somebody wants to change the neighbors for this graph node, we want them to use the methods for our data type here rather than manipulating the list. So we want to return a read-only list of the neighbors of the node. Now we can do that by just making a new copy of the list and returning it, but we can also do it the way shown here. So we can return neighbors as read-only, and you'll notice that the return type here is not a list, it's an iList. It's an interface to a list. And an iList actually does not contain the methods to modify the contents of the list. You can still walk the list and do all kinds of things with the list, but you can't add and remove things from the list. So this is the way that we return a read-only list of neighbors to whoever wants that list. Before adding a neighbor, we check to make sure we don't already have an edge to that neighbor. Now, if in fact the edges had weights on them, in other words, there was some cost associated with following the edge, then we might want to allow multiple different edges between two specific nodes. But this is an unweighted graph, so each edge costs the same to traverse, so we don't allow duplicate nodes. And if we find a duplicate neighbor, we just return false. We say, no, we didn't add that as a neighbor. Otherwise, we just add the provided node to our list of neighbors and return true. We can remove a neighbor by removing that node from the list of neighbors. And it turns out that this list method actually will return false if the neighbor isn't contained in the list, so that takes care of us returning false if there's no neighbor that they're trying to remove. We provide a method to remove all neighbors, and this is helpful, as we'll see when we get to the graph class. When we want to clear the graph, we actually want to remove all the references between the nodes in the graph, so the garbage collector can pick those nodes up when the garbage collector decides to collect the garbage. And finally, we have a method to convert the node to a string, providing the value and the list of neighbors for the node. The graph class is also generic, and the only field it has is the list of nodes in the class. The constructor doesn't do anything. We have a count property to return the number of nodes in the graph. And we have a way to access the list of nodes in the graph, but again, we return that as an iList, a read-only list, so that a consumer of the graph can't actually change the nodes in the graph by manipulating that list. They need to use add node and remove node methods here in this graph class to manipulate the nodes contained in the graph. We have a clear method that first removes all the neighbors for every node so that we're releasing all those references between the objects. And then we remove all the nodes from the nodes list. So once we're done with this, all the nodes have been disconnected from each other and all the nodes have been removed from the graph. To add a node to the graph, the first thing we check is to see if the graph already has that node. This particular graph that I've implemented doesn't allow duplicate values. So if you think of this as sort of representing specific cities, you wouldn't have the same cities included in the graph, like the same values, the same location, right? We just need one node for that particular location. There are certainly scenarios where you might want to allow duplicate values, but I don't allow them in this particular graph. And we'll look at the find method soon, but basically the find method returns the node for the given value. So if that's not null, there is already a node for this value, so we return false because it's a duplicate value. Otherwise, we add a new graph node with that value to our nodes list and return true. Another thing we might want to do is add an edge between nodes of particular values. So we first find both those nodes that we're trying to connect. If either one of them is null, we return false because we can't add an edge to a node that doesn't exist. We also check to see if the node 1 neighbors already contains node 2. In other words, there's already an edge from node 1 to node 2. And if that's the case, the edge already exists and we return false. Finally, if everything's okay, we add node 2 as a neighbor to node 1, and we add node 1 as a neighbor to node 2. So this is an undirected graph. There's no direction to the edges, so we need to add each of the nodes as a neighbor to the other. In a directed graph, we'd be adding an edge from node 1 to node 2, for example, so we'd only have this line of code, not this line of code. But in an undirected graph, the common way to do this is connect both sides. We can remove a node with a particular value from the graph. The first thing we try to do is find the node with that value. If we can't find it, that node is not in the graph, so we return false. Otherwise, we do a few things. We remove the node from the list of nodes for the graph, and we also walk through each of the nodes in the graph, and we remove this node as a neighbor from those nodes because we don't want a linkage, an edge, to this node that we're taking out of the graph. We can also remove edges between two nodes. We first find those nodes. If one or both of them don't exist, we return false because there can't be an edge between them because one or both of them doesn't exist in the graph. If node 1 doesn't have node 2 as a neighbor, there isn't an edge, so there's nothing to remove, so we return false. And finally, if we get here, everything's okay. So we remove node 2 as a neighbor for node 1, and we remove node 1 as a neighbor for node 2. And again, we do both of these things because this is an undirected graph. If this were a directed graph, we would only do this one. We look for a graph node with a given value by simply iterating over the list of nodes in the graph, and if in fact the value equals the value that was provided, we return that node. If we get all the way here, we couldn't find that node, so we return null. And the last thing we have is the toString method to convert a graph to the list of nodes that are in the graph. To recap, in this lecture, we learned how to implement graph and graph nodes. We saw how to provide read-only access to a collection, and we saw how to support garbage collection when we clear a graph. In this lecture, we'll complete our algorithm analysis for our graph and graph node classes. We'll start by analyzing the complexity of the graph node operations. So we'll scroll down to adding a neighbor. The neighbors contains method, which is a list method, is order n, where n is the number of items in the list. This is constant time. Adding a neighbor is either order 1 if we don't have to expand the list, or order n if we do have to expand the list. And this is constant time. But this we know is always order n, so the add neighbor operation is order n, where n is defined as the number of neighbors for the node. Removing a neighbor is also order n because the list remove method is order n. It does a linear search to find the neighbor to remove, so in the worst case it goes all the way to the end before finding the neighbor or not finding the neighbor. So the remove method is an order n method, so the remove neighbor operation for graph node is also order n. Removing all neighbors is order n. The remove at method, because we're removing from the end of the list, I've written this for loop to go backwards, not forwards. So we're removing from the end of the list each time, and that's a constant time operation because nothing in the list has to get shifted around once we remove the graph node. So the body of the loop is order 1, but this for loop executes n times, so the remove all neighbors operation is order n because we need to remove each of those neighbors. So it's order n, where n is defined as the number of neighbors. The toString method is also order n, where n is the number of neighbors, because of this for loop that executes n times, once for each neighbor. For the graph, it is common for people to specify complexities for graphs using v for the number of vertices in the graph and e for the number of edges in the graph. So even though we have typically been talking about order n, where n would be, say, the number of nodes in the graph, we'll be consistent with common convention for graphs and will express our complexities in terms of v, and I'll point out one place where e might give us a better result when we get there. So we'll start with the clear method. The remove all neighbors method for a graph node is order n, where n is the number of neighbors, but in the worst case, a node could be connected to all other nodes in the graph, including itself. So in the worst case, n is actually v, the number of vertices in the graph, so the body of this first loop is order v. We also are going to iterate over all the vertices or nodes in the graph, so this outer loop is order v as well. The way we calculate the complexity for this loop as a whole is we take the complexity of the loop body and we multiply it by the complexity of the loop itself. And we do that because for each iteration, we might get the worst case here. So this is order v, and this is order v. So this is actually order v squared. V times v is v squared. This bottom for loop, the list remove at method, because we're removing from the end, again going backwards, is constant time. So constant time times order v, because this touches every vertex in the graph. So this loop is order v. So we have an order v squared loop and an order v loop. So the complexity of the clear operation is order v squared, because v squared dominates v and we can just throw the v away. Now, the worst case for removing all neighbors is actually based on the fact that this is what's called a dense graph. So there are lots of edges relative to the number of nodes or vertices in the graph. In a sparse graph where we have fewer edges, this is really pessimistic, right? Because in fact, this can't be v in the sparse graph. It's going to be much smaller than that. So one other way we can think about this is this inner loop is order e overall. We're going to, in the worst case, through all of the iterations of this outer loop, we're going to do 2e removals because the edge is actually contained in both nodes to connect to the other node. So if we want to be a little more precise, we can say this first loop is order v times e instead of order v squared. And so that's a little more fair for sparse graphs. For the rest of our discussion here, I'm just going to express everything in terms of v, because that is generally applicable to all graphs, whether it's sparse or dense. But you should recognize the fact that for sparse graphs, including an e term for the number of edges in the graph can give you a tighter upper bound on the complexity of doing stuff on the graph. To add a node, we will actually discover that the find method is order v once we go analyze that. So order v, constant time, adding to the list is either order 1 if we don't have to expand the list, or order v if we do. And then this is constant time. So this is clearly the dominant factor. It's order v. So adding a node to the graph is order v. Adding an edge between two nodes. I just said that the find operation or method is order v. So these first two lines are order v. And then we have some constant time stuff. And then checking a neighbor to see if that edge already exists is in fact order V in the worst case for a complete graph. We'd have to walk a list of neighbors that contained V different entries for all the nodes in the graph. So this is also order V, and this is constant time. So we saw before when we added a neighbor to a graph node that if we needed to expand that list of neighbors, then it was order n, where n is the number of neighbors. And here for a complete graph, we're going to say, or even a dense graph, we're going to say this is order V. So we have a bunch of order V's, but none of them are nested inside another one. So there's no multiplication here. There's just a bunch of adding. So the add edge operation is order V. For the remove node operation or method, this is order V. We have a bunch of constant time stuff. Removing an item from the list is order V because the list remove method does a linear search for that item to remove. So node remove neighbor is order n, where n is the number of neighbors for the node. So we'll say order V for a dense or complete graph. So the body of this loop is order V, and the loop executes V times, one for each vertex or node in the graph. So we have to multiply this order V by this order V, which tells us that the remove node operation is order V squared. Removing an edge, order V, constant time, order V, constant time. Removing each neighbor is order V as well. And because all these order V's are added together, the remove edge operation is order V. The find simply does a linear search of the graph nodes. So this is order V because this loop executes in the worst case V times. And finally, converting to a string is also order V because we convert each node in the graph to a string. To recap, in this lecture we got more algorithm analysis practice. We discovered that the complexity of algorithms on graphs are regularly expressed using V, the number of vertices in a graph. And we also learned that using both V and E, the number of edges in a graph, can give us a tighter bound on the complexity for some algorithms on sparse graphs. In this lecture, we'll practice working with dictionaries. And we looked at several dictionaries in the Feed the Teddies module in the previous course, but this time we'll create and use a dictionary from scratch. And we're doing that because we'll discover in the next lecture that dictionaries can help us when we're searching a graph. In this example, we're going to create a dictionary of high scores keyed by the gamer tag, and then we'll prompt for and get a gamer tag from the user, and then we'll print the high score or an error message. So if the dictionary contains a high score for the given gamer tag, we'll print that high score out. But if the dictionary doesn't have a high score for the gamer tag, we'll print a different message. The way we declare a dictionary is we say dictionary, and we immediately discover that dictionary is not available to us at this moment. That's because the dictionary class is in the system collections generic namespace. So we need to add a using directive to get to that class. The next step is that a dictionary has a key type and it has a value type. So we're going to key by strings and we're going to save the values that are keyed by the strings as ints. Remember, in player prefs, we could only key by string and we could only save strings, ints, or floats. In the dictionary class, we can key by any data type we want and we can store any data type we want as well. I will call this high scores. And of course, we need to create a new dictionary object. The next thing we need to do is actually add items to the dictionary. So we do that using the add method, and we provide a key. So let's say Joe has a high score of 100, and Bob has a high score of 9001, and their less adept brother Joe Bob has a high score of 1. Okay, so this puts these 3 items into the dictionary using Joe Bob and Joe Bob as the keys, and 100, 9001, and 1 as the values. Now we'll prompt for it and get a gamer tag from the user. And finally, we will print out the high score or the error message. So the way we check if a particular key, specifically the gamer tag the user entered in this case, is actually in the dictionary is we use the contains key method. And this will return a Boolean, as you can see from the pop-up, and it says we need to provide a string as the key because this particular dictionary has string keys. And gamertag is a string, so we will provide that. Let's do the error condition first. We'll say no high score for, and then we'll tell them what they entered. So we can actually test this now. We can just enter some gamer tag that's not in the dictionary, and we get no high score for that gamer tag. If the gamer tag is in the dictionary, then we can say something more interesting. High score for the gamer tag they provided is, and now we need to retrieve the value in the dictionary for the gamer tag key, and the way we do that is very similar to the way we've accessed elements in arrays and lists. We just use square brackets and we put gamer tag between them because gamer tag is the key. I will fix that typo I noticed as I was typing, and now we'll control F5, and if we enter Joe, we extract Joe's high score, and I'll show you the other two as well. Bob has 9001, and poor Joe Bob only has 1. So that's how we declare a dictionary variable, add elements to that dictionary, and retrieve those elements, and also check to see if the dictionary has a particular key. To recap, in this lecture we were reminded that dictionaries store values using a key, and we practiced creating and using a dictionary, and we also learned how to use the contains key method to determine whether or not a dictionary contains a specific key. In this lecture, we'll learn how we can search a graph for a path from one node to another. We can't just use the graph find method because that method simply returns a node with the value that we provide. And we don't want a reference to our target node. We actually want a path from our starting node to that node. This is obviously a really useful thing to be able to do if you have AI that needs to do pathfinding in your game. First, we'll look at how the searching is implemented, and then we'll actually see how it works for both depth-first search and breadth-first search. So our main method builds a graph and then does a number of searches. Think of these as test cases if you'd like. And here's building the graph. So we have a number of nodes and a number of edges, and this is just like the picture I showed before we started looking at the code. And here's the meat of the work here is searching the graph, and we provide the value at the start node and the value at the finish node. We provide the graph we want to search, and we provide search type. And search type is just an enumeration that tells whether it's depth first search or breadth first search. We create a search list, which is a linked list of graph nodes. So this is the list of nodes that we need to search as we try to find a path from start to finish. We have a couple of special cases to look at. So if the start node is the same as the finish node, we're already there. So we just return start to string because the path to the finish node is just stay where you are. If either the start node or the finish node isn't in the graph, then there's no way for us to get from start to finish. So we return an empty string as the path from the start node to the finish node. And finally, we get to the part that does an actual search. So the first thing we do is, this is an int value, remember? Although, of course, with a generic graph, it could be any value, but this example is with ints. And so we find the start value in the graph, and we put it into start node. Then we create a dictionary that's keyed by graph nodes, and the value is path node info. So let's go briefly take a look at path node info. This is a tiny class that just has a reference to the previous node. So we have a constructor that will create this path node info, and we allow access to the single field in the class. So the big idea here is, when we're done, when we've found our way through the graph from the start node to the finish node, we need to be able to say, here's how I got there. And the way we'll do that is the end node will point to the node just before it in the path, and then that node will point to the node just before it in the path, and so on, all the way back to the start node. So basically we can follow these references backwards from the end node to the start node, and once we have that information, we can just build the path in the correct order over here in the class that does the search. Now I certainly could add that previous reference to graph nodes, but that would kind of break the graph abstraction, wouldn't it? Because graphs aren't about paths between nodes necessarily. That's one of the things we can use graphs for, but it's not the only thing we can use graphs for. So we're attaching a little extra information, and we're not even doing it in a new class that contains both the graph node and a reference to the previous node. We're just storing it in a separate place, and that separate place is this dictionary. And we'll actually find another great use for the dictionary a few lines of code down from here. So we add to the dictionary using start node as the key, and start node points to null because it's at the very beginning. So there's no previous node for the start node in our path from start to finish. Finally, we add start node to that list of nodes that we need to explore as we try to find a path from start to finish. Okay, now we go to while loop, and as long as there's a node to look at, then we will keep looping. We take the front of the search list, so here's search list, which is a linked list, and we take first, so that's the front, and we access the value, so that's the actual graph node that the linked list holds, and we put it in current node, and then we take that node off the front of the list. We're about to explore it, so we don't need to keep it in the list anymore. Now we're going to look at each neighbor of the current node that we're looking at. If that neighbor is the finish, then we found a path, and we'll add the neighbor to our path nodes dictionary, making sure that it points back to the current node so that we can retrieve the path. And then we call convert path to string, which we'll look at when we're all done with the rest of the search. Here's that other great use of the dictionary. We can check to see if path nodes contains the key for the neighbor. If it does, we've already taken a look at neighbor, and that means we've just hit a cycle in our graph, and so we are just going to skip this neighbor. We're not going to do any additional processing for it. We're just going to jump over it, and continue, which we haven't seen yet, just says go to the next iteration of the while loop. We don't want to break out of the while loop. We want to keep processing the search list, but we want to continue directly to the next iteration of the while loop. And so this is the way that we protect ourselves from getting caught in cycles in the graph. And dictionaries are super fast for finding out whether they contain a key. So that's a good way to check for cycles. Finally, this is a regular neighbor. So we're going to link the neighbor in the dictionary to the current node. And then we're going to add it to the search list. And it turns out that for depth first search, we add to the front of the search list. And for breadth first search, we add to the back of the search list. And this is the only thing we need to do differently between depth first and breadth first search through the graph, looking for that path from start to finish. This is a debugging write line so we can see what's happening. And if the while loop runs until there's no more search nodes and we haven't returned yet, then we didn't find a path, and so we return the empty string. Here's that convert path to string method. So we're going to build a new linked list for the path, and we're going to add the end node first at the front of that list, and then we will look at what node came before it. And while we haven't reached the end, so when we get to the start node, previous will be null, but before that, we'll just be following our way backwards through the path. We add to the front again. This is how we're reversing the order. We add to the front again, and we move along the list. And then finally, we just do a forward loop through the path to turn those graph nodes into strings. So here's where we reverse the order of the backwards previous links into the forward path from start to finish. Okay, let's see how this actually works, and we'll start by looking at depth first search. I'll run it to show you that this is real code that actually works, so there are all the test cases that execute, but we're actually going to look at some PowerPoint for depth first and breadth first search. Okay, in both cases, we're looking for a path from node 4 to node 1. So when we start, we put the start node, the node 4, onto the search list, and that's the only thing on the search list at this point. Then we pull it off the search list, and we look at each neighbor, and both 11 and 42 are neighbors, and they are not the finish node, and they are also not a cycle in the graph. So we put both of them on the front of the list, and it turns out that in this order, it's 11 and then 42. So now 42 is on the front of the list, and we pull it off the front of the list, and we look at both neighbors, and neither neighbor is the finish, and neither neighbor is a cycle. So we put them both onto the search list again, and then we do one more iteration, and we find that 5 has the neighbor 1, which is the finish, so we're all done. And our path is 4, 42, 5, and 1. Now, that was actually just dumb luck that the order worked the way it did, because we certainly could have sort of wandered around the graph a little more. So the big idea is that we are going deeply into the graph as far as we can, looking for our finish, and if we don't find it, then we're going to back up and look further and so on. So it's called depth first search because we sort of go deep first. We pick a node to expand and we do all its children, and then we pick a node to expand and do all its children, and that happens because we're putting the nodes onto the front of the search list. Breadth first search works differently. So we start with 4 again, and then we add both children, so this all looks the same so far, but remember we put those children on the back, not the front of the search list. So the next time through, we actually add all of the children of both those nodes. So essentially, what we're doing is we're going one level into the graph from the start node, then we're going another level into the graph from the start node, and then we go a third level into the graph, and that's where we find our finish node. So it turns out that in this simple example, we're getting both the same paths, but it turns out that breadth first is guaranteed to find the shortest number of edges you cross to get to the finish node, while depth first may not. Certainly in a more complicated graph, you might find a longer path that leads from start to finish because you decided to pick the wrong edges to follow as you went deeply rather than broadly through the graph. To recap, in this lecture, we learned how we can use a linked list and a dictionary to find a path from one node to another in a graph. We also learned how to avoid getting caught in a cycle in the graph. And finally, we learned the difference between depth-first search and breadth-first search. What will you learn about in the stack lesson? You'll learn what a stack is, and as usual, we'll go look at a picture. So as you can see here, we have a stack of values, and the only place we interact with the stack is at the top. So if we want to add something to the stack, we push it onto the stack. And if we want to remove something from the stack, we pop it from the top. And regularly we're allowed to peek at the top of the stack as well, but we can't see anything else in the stack except the value that is on top. Given that, you should do an in-video quiz. And the answer is a stack is a last in, first out, or LIFO data structure, because the last thing that we added to the stack, got pushed on the stack, is the first thing that we remove from the stack when we pop it from the stack. We'll also learn how to implement a stack, and we'll learn the algorithmic complexity of the stack operations. In this lecture, we'll implement a stack. In practice, you should just use the stack class that's available in the System Collections generic namespace, but implementing a stack ourselves gives us more programming and algorithm analysis practice. Our stack is of course a generic as usual, so we can store any data type in our stack, and the underlying structure that holds the contents of the stack is just our standard list from the System Collections generic namespace. So our constructor doesn't do anything. Our count property just tells us how many items are in the stack. And you'll notice there's no way to get the contents of the stack. The data structure enforces the fact that you can only get at the top of the stack. You can't sort of work your way down through the stack doing something. You can only see the top of the stack. For our methods, we can push onto the stack, and this is really easy. We just add something to the stack. Now the list add method adds the item we've provided to the end of the list, so we are thinking of the end of the list as the top of our stack. And you should go do an in-video quiz about pushing onto the stack. And the answer is, of course, it's perfectly fine to push onto an empty stack. That's how we get stuff onto the stack. We start with an empty stack, so pushing onto an empty stack is fine. We can also pop from the stack, which means take the top item from the stack. Now, if the stack is empty, then popping is not a valid thing to do. There's an empty stack, so you can't get the top of an empty stack. So we actually throw an exception here, an invalid operation exception that says you can't pop from an empty stack. But if the stack does have something in it, we first access the end of the list that holds the contents of the stack, and we save it. And then we call remove add on the list, which takes away that last item in the list, the top of the stack. And we need to do it with these two steps because the return type for the removeAt method is void. So if we want access to that item, we need to save it before we take it out of the list. And then finally, we return that item. Given that, you should go do an in-video quiz about popping from the stack. And of course, you can't pop from an empty stack. That's a bad thing because there's no way to get that first element from the stack. The way peek works is we are looking at the top of the stack, but we are not actually removing the top of the stack. So again, if the stack is empty, there's nothing to peek at. So we throw an invalid operation exception saying you can't peek at an empty stack. Otherwise, we simply return the top of the stack. Notice we're not removing it from the list. We're just returning that item for the consumer of the class to do whatever they want to do with it. And you should do an in-video quiz about peeking at the top of the stack. And the answer is no, you're not allowed to peek at the top of an empty stack. And the last method in the class simply converts the stack to a string. Now you wouldn't typically let people do this because that does expose the entire contents of the stack, but it's certainly helpful if we're testing and making sure that the stack is working properly. And of course there is a test stack class that runs through a bunch of methods testing the stack to make sure it works properly. To recap, in this lecture we saw how to implement a stack, and we also saw how we can enforce the rule that consumers of the stack can only manipulate the top of the stack. In this lecture, we'll complete the algorithm analysis for the operations, the methods, in our stack class. We'll start with the push method, and the push method simply calls the list add method, which we know from our previous algorithm analysis is order 1 if we don't have to expand the list, and order n if we do have to expand the list. And so we often call this order 1 amortized, but in the worst case, this is order n. And you should go do an in-video quiz to make sure you understood that. For the pop operation, this is a constant time operation. This is a constant time operation. Looking at the end of the list is a constant time operation because we can access any element of a list in constant time. The removeAt method is constant time because we're moving from the end of the list. If we were actually moving from element 0, we would be paying an order n cost, where n is the number of things in the list, because every other element of the list would have to get shifted down one. So this is actually one of the benefits of using the end of the list as the top of the stack, is that we get constant time for the removeAt, and of course return is constant time as well. So you should now go do an in-video quiz saying what the complexity of the pop operation is. And because it's all constant time in here, it is an order 1 operation. The last one to look at is peek. And again, constant time, and constant time. So you should go do an in-video quiz about this. And the answer is this is also constant time. So this is pretty efficient as a data structure. Pushing is mostly constant time unless we have to grow the list that holds the contents of the stack. Popping is constant time and peeking is constant time. We do convert to the string, and this is of course order n because we have to look at each element in the stack to print it out. But remember, this toString is for debugging because we don't really want to expose to consumers of the class what all of the elements in the stack are. We want to enforce that they can only see the top of the stack. To recap, in this lecture, we got more algorithm analysis practice, and we also learned that pop and peek are always constant time, order 1 operations, and push is usually an order 1 operation specifically when we don't have to expand the list that we're using to store the contents of the stack. Here's what you'll learn about in the queues lesson. You'll learn what a queue is, so let's go look at a picture. As you can see, we add things to the back of the queue, and we take things off the front of the queue. So adding to the back of the queue is called enqueuing a value, and taking something off the front of a queue is called dequeuing a value, and we can also peek at the front of the queue as well. But just like with the stack, we can't actually access the internals of the queue. We can't get at all the values in the queue. We actually can only add to the back and take from the front and peek at the front as well. Given that, you should go do an in-video quiz. And the answer is queues are first in, first out, or FIFO data structures, because the first item that's added to the queue by enqueuing it at the back of the queue is also the first thing that's removed from the queue when we dequeue from the front of the queue. Now, you should go do another in-video quiz about something we haven't even discussed. Well, priority queues are like regular queues, except that the elements are not just ordered in the queue based on when they were added, but they're also ordered based on the priority of that particular item in the queue. And that can be pretty useful when we're doing messaging systems or figuring out as an AI player which items we should go after first based on the value of those items. We will also learn how to implement a queue, and we'll learn the algorithmic complexity of our queue operations. In this lecture, we'll implement a queue. In practice, you should just use the queue class that's provided in the System Collections generic namespace, but implementing our own queue gives us more programming practice and more algorithm analysis practice. If you need a priority queue, which we're not implementing today, but which is discussed in the queues reading, then you have to implement your own. As usual, our queue is a generic, and we are using a list to hold the contents of the queue. The constructor doesn't do anything. The count property returns how many elements are in the queue. So the first queue operation for us to look at is enqueue, which means put something onto the queue, and even more specifically, put something onto the back of the queue. So we add to the list of items in the queue, and we know that the list add method adds to the end. So in this case, unlike in the stack where we treated the end of the list as the top of the stack, we're treating the end of the list as the back of the queue and the front of the list as the front of the queue. So you should go do an in-video question about enqueuing onto an empty queue. And the answer is, of course, we should, because that's how we get stuff into the queue. Removing an item from the queue is called dequeue. That's what we're talking about. And so we remove an item from the front of the queue. If the queue is empty, we can't remove anything from it, so we throw an invalid operation exception, can't dequeue from an empty queue, and now would be a good time for you to go do an in-video quiz about this. And of course, we shouldn't. It's impossible to take something out of an empty queue. If the queue isn't empty, then we will save the item at the front of the queue, the very first item in the list, and then we will remove that item from the list because we've dequeued it from the queue, and then we return the item. Our last operation is peek, and before I even scroll down, you should do an in-video quiz about peeking at an empty queue, and we really can't. So if the queue is empty, then we'll throw an exception saying you can't peek at an empty queue. If the queue isn't empty, then we will return the first element in the list which is the front of the queue. And of course, we're not removing it from the list. We're just returning it so the consumer of the class can take a look at it and do whatever. We do have a toString method here as well. And just as for the stack, this is really just for testing because we don't want to expose to anyone what all of the things in the queue are. They really can only do three things. They can add something to the end of the queue, they can look at the front of the queue, or they can dequeue something from the front of the queue. So just as for a stack, we can really only look at the top of the stack, for a queue, we can really only look at the front of the queue. To recap, in this lecture, we learned how to implement a queue, and we also learned how to enforce the rule that a consumer can only add items to the queue at the back of the queue and can only remove items from the front of the queue and also can only peek at the front of the queue. In this lecture, we'll complete our algorithm analysis for the operations, the methods, in our queue class. We'll start with the enqueue method that adds an item to the back of the queue. So pause the video if you need to at this moment to look at the code here, and then go do an in-video quiz about the algorithmic complexity of the enqueue operation. And the answer is, if we don't have to grow the list, it's order 1, and if we do have to grow the list, it's order n. So you can either say it's order 1 amortized, or you can say it's order n, because that is the worst case. For dequeue, we know we can't dequeue from an empty queue, so we check that first, and then we access the front of the list and then remove the front of the list and return the item. So again, pause the video if you need to think about this, and then do an in-video quiz about the algorithmic complexity. Well, it turns out that this is constant time, and this is constant time, and this is constant time, and darn, this one is not. Remove at is going to be order n, because we're removing the very front of the list, and that means that all the rest of the items in the list get shifted down one. So dequeue is actually an order n operation. Now you might think that that just means we made a poor decision, that the front of the list will be the front of the queue, and that we should have made the front of the list the back of the queue, just like we did when we were using the back of the list as the top of the stack. The problem with that approach with the queue, because we deal with both ends, adding at one end and removing from the other, is if we did that, then enqueuing would no longer be doing this. We'd actually have to figure out a way to add to the front of the list, which would mean that everything in the list would have to get shifted up. So we would be making it so enqueue is an order n operation, so that dequeue would be an order 1 operation. Because the list class doesn't give us a way to add at a particular location, that's harder work than it's worth. So we might as well just leave it the way we have it and just pay the order n cost when we dequeue an item from the front of the queue. Finally, peeking at the front item on the queue, you should already know this, but go do an in-video quiz about the complexity. And the answer is order 1, because order 1, and order 1 constant time to access a particular element of the list. To recap, in this lecture, we got more practice doing algorithm analysis, and we also learned that peeking at a queue is always constant time, an order 1 operation, but one of the dequeue or enqueue operations is going to have to be order n, because we interact with both the back of the queue to enqueue something and the front of the queue to dequeue something. This lesson is all about trees. So what will you learn in this lesson? You'll learn what a tree is. So let's go look at a picture. Here's a small tree that displays the characteristics that are important for trees. First, we have a root, and the root is typically shown at the top of the tree. I know that seems backwards, but that's where the root goes. So the node marked 4 in this picture is the root of the tree. Each node can have 0 or more children. Each child can only have one parent, and there are no cycles in the tree. A little more terminology. A node that doesn't have any children is called a leaf node, and a node that has one or more children is called a branch node. We'll talk about recursion, which is a very useful technique for traversing trees. We'll implement our own tree node and tree classes because C# doesn't provide those to us. We'll do algorithm analysis of those tree node and tree classes. We'll see a number of different ways that we can traverse a tree, and we'll explore a technique called minimax searching, which is a useful way to figure out the best move you can make in an adversarial two-player game. In this lecture, we'll learn about something called recursion. So what is recursion? It is a technique that we use to solve a problem by solving smaller versions of the same problem. The other characteristic of problems that are well suited to be solved using recursion is we need to have a base case or a termination condition to stop the recursion. In other words, a version of the problem that's small enough that we know the answer without trying to solve even smaller versions of the problem. How do we do recursion in C#? Well, we have a method, call itself, with a smaller version of the problem that we're trying to solve. And we also have the method recognize the base case so it can stop recursing and return the answer back up so we can finally build the final solution out of the solutions to these smaller versions of the problem. Why do we care about recursion? Well, recursion is really useful when we traverse trees. So we'll see ourselves using recursion both in our implementation of the tree class and as we learn about traversing and searching trees. I'm using Visual Studio for this lecture because I can use the debugger in a console app to show you what's happening with the call stack. I can't do that with MonoDevelop because the MonoDevelop that ships as part of Unity, the debugger doesn't work in the console apps. So just for this lecture, I'm using Visual Studio. So let's look at our factorial method that works recursively. Here it is. It's a very short method. What we do is we pass in an n, the number for which we want to calculate the factorial, and if n is equal to 0, then we're going to return 1 because the mathematicians have told us that 0 factorial is 1. And if it's not, then we're going to return n times factorial of n minus 1. So if in fact we're calculating 5 factorial and we call this method with 5, then we will return 5 times 4 factorial. And then it will be 4 times 3 factorial and so on until we get all the way down to n equals 0. And that's our base case or our termination condition. So let's watch how this works. I'm going to set a breakpoint here. And up here in the main method, we're going to just provide an n, and then it will calculate the factorial for us. So I'm going to run the code using F5, not Control F5, so I'm using the debugger. And I'm going to enter 5 factorial. So as you can see, we hit this breakpoint, and n is 5 here. And down here in the call stack, we have just added this call to the factorial method. Now I'm going to F5 again, and as you can see, n is now 4, and our call stack includes the first call to the factorial method and the second call. and I'm going to F5, so n is 3, and F5 and n is 2, and F5 and n is 1, and F5 and n is 0. So here you can see n is 0, and here in the call stack, you can see all these calls to factorial. So an interesting tidbit is if in fact we end up with infinite recursion, we will just keep calling this method again and again and again, never reaching the base case. And so eventually our call stack will get filled up and the stack will overflow. And that's why the Stack Overflow website is named Stack Overflow, because you go there when you have programming problems, and overflowing the call stack with infinite recursion would be a programming problem. Okay, so now we have reached our base case. So I'm going to step instead of F5. I'm going to step. And as you can see, I'm going to return 1. So if I F10 here, I get to the end of the method, and I've just removed one of those calls from the call stack. I just returned 1 and returned back here. So n is 1, and I've just returned 1 from the call to factorial with n of 0. So as you can see, once I come out of all of those recursive calls, I get the answer 120, which is in fact 5 factorial. So I'll exit out of here by entering a -1. So the big ideas here in this recursive method are, I can keep breaking the problem into smaller versions of the problem to try to solve it, as long as there is a base case or a termination condition that I get to stop the recursion. To recap, in this lecture, we saw how we can do factorial calculation using recursion, and we also learned that recursion will be useful as we work with trees, and you didn't necessarily learn that, I just told you that, but trust me, it's true, and we'll see that it's true in a few lectures. In this lecture, we'll look at another problem that we can use recursion to solve. Specifically, we'll see how we can do binary search using recursion. We will again use Visual Studio so we can use the debugger to look at how recursive binary search works. So we'll walk through one of these where we have an array of 1, 3, 5, 12, 17, 21, 33, 42, 42, and 42. And we are going to do a binary search of this array. So we are going to pass in the number we're looking for, which is 3. We're going to pass in the array we're going to search. We'll pass in the lower bound, and we'll pass in the upper bound. So we start with a lower bound of 0 and an upper bound of the array length -1. We start by saying we need to search the entire array. Let's go look at the binary search method to see how it works. So as I said, we pass in a search value and the array and a lower bound and an upper bound. And we are going to recurse until one of two things happen. So we have two base cases in this particular case. One of those base cases is that there's nothing else to look at, and that is the case. When lower bound is greater than upper bound, then there's nothing else for us to look at, so we return -1 because we didn't find the value we were looking for in the array. We also might have found the search value when we look at the middle location. And so if we've found the value, we return its location. And here's where the recursion comes in. If in fact the middle value is greater than search value, then we know that the value we're looking for is on the left. So we make a recursive call to the method. We're still looking for search value, and we're still looking for it in the search array. We leave the lower bound the same, but we set the upper bound to middle location -1. So now we're looking at a chunk of the array to the left of middle location. Similarly, if the middle value is less than search value, then we are going to search for the value in the array, but this time we're going to look to the right of middle location, so our lower bound gets moved up to middle location +1, and our upper bound stays the same. So let's use the debugger to watch what happens. I'll set a breakpoint here in the binary search method, and we will start debugging with F5. So we are looking for the value 3, and the call stack shows our first call on the binary search method. Our lower bound is 0, and our upper bound is 9 because we have 10 elements in the array. I will F10 a few times. So we're calculating the middle location. And down here on the left, you can see that the middle location is 4 at this point. And we F10 one more time. And middle value is 17. So we know 17 is greater than the 3 we're looking for. So we are going to keep searching. I'll F5. So you can see over here in the call stack, we're in our recursive call on the binary search method. At this point, lower bound is 0 and upper bound is 3. So I'll F10. And I'll F10 one more time. And middle location is 1 and middle value is 3. So we've actually just found with one recursive call, 2 calls to the binary search method, but one recursive call to the binary search method where we changed upper bound. So we were shrinking the conceptual size of the array that we were searching for the element each time we called the method. And so this is our first base case. I'll F10 to show you that we in fact are going to return middle location because we found 3, which is what we were looking for. I'm going to F5 again, and I will tell you that this time we are searching for the value 43, which is not in the array. So we start with our lower bound of 0 and our upper bound of 9. And I will F5, and you'll see in the call stack, this is our first recursive call. And because 43 was greater than 17, we are now going to change our lower bound to 5 and our upper bound to 9. Let's see what that middle value we're comparing to is. It's 42. And 43 is greater than 42. So I'm going to F5 again. Here you can see in the call stack, we're now in our second recursive call to binary search. Lower bound is 8, upper bound is 9. We're going to find 42 again, so I'll F5 again. Here you can see lower bound and upper bound are both 9. And we're in our third recursive call to the binary search method. I'll F5 one more time. There's our last recursive call. Lower bound is 10 and upper bound is 9. So I will F10 to show you that we're returning -1 here because we hit the other base case for the recursion where there was nothing else to look at and we didn't find the value we were looking for in the array. To recap, in this lecture, we saw how we can do a binary search using recursion. In this lecture, we'll implement a tree. And C# does not provide a tree class to us, so if you need a tree, you need to build one yourself. We'll start by looking at the tree node class, which is of course a generic. It has 3 fields. It has the value we're storing in the node, it has a reference to its parent, and it has references to each of its children in a list. So you can think of this as like a doubly linked list. Remember, a singly linked list, each node only points to the next node in the list, whereas in a doubly linked list, each node pointed both to the next node in the list and the previous node in the list. It's actually helpful to have a node point to its parent as well as to its children. So I have links both up and down the tree between the nodes in the tree. The constructor, we pass in a value and we pass in our parent. So for the trees I've implemented, the nodes have to have a parent And of course, the root node in a tree will have null as the parent. But when we create a tree node that we're going to add to an actual tree, we want to indicate what parent that node has so we can hook it into the tree correctly. So we set the value field and the parent field to the parameters that were passed in, and we create a new empty list of children. For the properties, we can get the value. We can both get and set the parent, and we'll see where those things happen in the tree class. And we provide a read-only list of the children of the node. And this is the same technique we used in our graph node class to provide a read-only list of the children for a graph node. The add child method makes sure we don't add a duplicate child. We don't allow self loops. In fact, trees are acyclic. We can't have cycles in a tree, and we certainly can't have a cycle from a node to itself. So we don't add the self as a child. But finally, if we can add a child, we add the child that was passed in to the list of children for this node, and we also set the parent for that child to this node, and then we return true. We might want to remove a child, and if we do, we check to make sure our list of children contains the child to be removed, and if it does, then we null out the parent for that child because that child is now parentless, because remember, nodes in a tree can only have one parent. So if we are disowning this child, if we're removing this child node as a child of this particular node, then that child no longer has a parent. And then we return the results of calling the list remove method for the child. If we get here, it means that the child that was passed in isn't a child of this node, so we return false because we can't remove a child that we don't have. We also provide a remove all children method, and that helps when we want to clear a tree so we can support garbage collection. And finally, we convert the node to a string. And we do that by saying what the value of the node is and what the parent of the node is. And so it could either be that the parent node has some value, or it could be that the parent is in fact null, like for the root node in a tree. And so we put null if that's the case, and then we append a list of all the children. The tree class is also a generic. It has two fields, a reference to the root of the tree, which starts as null, and a list of the nodes in the tree, which starts as an empty list. The constructor requires us to pass a value in, and that value becomes the root of the tree. And you'll notice that when we call the tree node constructor, we provide the value for the node, and we say null for the parent, because the root of the tree doesn't have a parent node, and we add the root to the list of the nodes for the tree. For the properties, we let a consumer of the class get a count of the number of nodes in the tree, and we also let them get a reference to the root of the tree, because it's very common, as we will see when we do tree traversal, it is very common to traverse a tree starting at the root. And you have to have a reference to the root before you can actually do that traversal. We have a number of methods. We can clear all the nodes from the tree. And to do that, we null the node's parents and remove all children. So this makes sure that there are no references between the nodes so they can be garbage collected. And then we take all of those nodes out of the nodes list, and we set root to null. So now the tree doesn't have any nodes and doesn't have a root, but all those previous nodes can be garbage collected. When it's time to add a node to the tree, we make sure the node isn't null, because that would be silly to add a null node to the tree. we make sure that the parent isn't null, because if the parent is null, we're trying to add a second root to the tree, and that would not be connected to the rest of the tree, and our tree has to be totally connected. And finally, we also make sure that the set of nodes for the tree actually contains the parent. So if the node is null, or the parent is null, or the nodes doesn't contain the parent, we return false. We can't add this node because it's defective in some way. So here's where we access the parent property of a tree node. So we move to the parent, and we access the list of children, and we check if that list of children contains the node we said we just want to add. Because if that's true, that means that this node is already a child of the parent, so we return false. And finally, we might be okay. And if that's the case, we add the node that was passed into the list of nodes, and we also call the addChild method on the node's parent because we want to add this node as a child of the node's parent. Removing a node from the tree is the most complicated method we have here. So if we pass in a null node to remove, we return false. We also check the special case where the node to remove is the root of the tree, because if it is, what we're really doing is clearing the tree. So we just clear the tree and return true. The else clause is the interesting part of this method. So the first thing we try to do is we try to remove the node as a child of that node's parent. And if that fails for some reason, for example, this node isn't actually a child of the parent, then we're going to return false. So we're doing some error checking along the way here to make sure each step of removing the node from the tree succeeds, otherwise we return false. After removing it as a child of the parent, we remove the node from the list of nodes for the tree. And again, if that wasn't successful, we return false. And here's where we actually have some recursion. So we check to see if we are actually a branch node. So if the number of children we have is greater than 0, then we're actually going to recursively prune the subtree that is rooted at this remove node. Remember, because each node only has one parent, as soon as we remove this node, all the nodes that are a subtree rooted at this node are no longer reachable from the root. There's no other way to link into those other nodes starting at the root. So we have to also prune each of those nodes out of the tree. So what we do is we get the children of the node we're removing, and we put them in this list. And then we iterate over this list, going backwards because we're going to remove stuff as we go along. And here's the recursive call. So this is one of the reasons we covered recursion. We use recursion here in our implementation of the tree class, and we also will use recursion when we do tree traversals in a couple of lectures. But this is the interesting chunk of this method because we see recursion in action to prune that subtree. We can look for a tree node with a particular value, and this should all look familiar to you. The only difference from what we've done previously is that we are actually allowing duplicate values in our tree. So we will just return the first node with the value provided that we find in the tree if we find one. And finally, we convert the tree to a string as well, and the root might be null, so we have to check for that. If it's not null, then we add the root value, otherwise we say the root is null, and then we go through the nodes in the tree, and we append each of those nodes, converting it to a string, to our string for the tree. And that's it for the tree class. To recap, In this lecture, we saw how to implement both a tree class and the tree node class we need to support that. And we also saw recursion in action in the remove node method. In this lecture, we'll complete our algorithm analysis on our tree node and tree classes. We'll start by looking at the addChild method in the tree node class. The contains method for a list performs a linear search looking for the provided argument, and we know linear searches are order n, so the question is order n in what? Well, order n in the number of children that this particular node has. This line of code is order n, where n is the number of children for the node. The rest of these things are constant time. Adding a child is order n if, in fact, we have to expand the list. And these two are obviously constant time. So we have order n here and order n here, which makes the addChild operation an order n operation. Removing a node, remember our discussion of contains, so this is order n in the number of children for the node. So this is order n, where n is the number of children for the node. We null out the parent, so this is constant time, but remove also does a linear search for the node, so this is order n in the number of children. And of course, this is constant time, so we have order n and order n, but including an order n operation inside an if statement that has an order n Boolean expression does not mean we need to multiply them together like we do when we have an order n operation inside a loop that executes n times. So this is still additive, so remove child is still order n. Removing all the children from the node, this loop is clearly order n, where n is the number of children the node has. This is constant time, and this is constant time only because we're removing from the end of the list, so we're avoiding any shifting as we go through the list removing stuff. So because the loop executes n times, the remove all children operation is order n. And then converting the node to a string is also order n in the number of children because we loop over each child, printing out its value. For the operations in the tree class, we'll start with the clear method, and let's look at the easy part first. So the easy part is the second loop that executes n times, and remove at is constant time because we're removing from the end of the list. So this chunk of code is order n. This line is constant time. So the question is, what about this? Well, clearly the loop iterates n times, where n is the number of nodes in the tree. This is constant time. We just talked about remove all children as being order n, but with a different definition of n. N was the number of children for that particular node. So we have to sort of think of this stuff all together. How many times will we actually remove a child from a parent? And it turns out that because each node can only have a single parent, we're only going to remove n children in total across all the iterations of this loop. We're only going to remove n total children inside. So we don't have to multiply an order n here times n here to get order n squared. It actually turns out that this is order n. So because this is order n, and this is order n, and this is constant time, clear is an order n operation. To add a node to the tree, this costs us order n in the number of nodes in the tree. This costs us order n in the number of children for the parent node that we're adding. And in the worst case, the parent is the root node and all of the children are siblings, they all have the root node as the parent. So in that worst case, this would also be order n in the number of nodes in the tree. Adding a node to the list of nodes is order n if we have to expand the list. And adding a child is order n, where n is the number of children that the parent has, which in the worst case could be n minus 1 children, where we have a very shallow tree where the root has all the children and nothing goes lower than those children. So we have a bunch of order n's here. So the add node operation is order n. Removing a node, remember, is the most complicated method we have in this class. Luckily, to start off with, we have some constant time stuff. We have order n for clear. We have more constant time stuff. We have order n for removing the child. We have order n for removing the node from the list of nodes, because the list remove method does a linear search. And then we have this interesting recursion stuff. So everything other than this recursion, which is to recursively prune the subtree, everything else is order n. So we can think of everything else as sort of the body of a loop. It's not really a loop, it's a set of recursions we're going to do, but we're going to do order n stuff on every recursion. So the question is, how many recursions are we going to do? And the answer is, in the worst case, we have a tree where every parent has a single node. So this is essentially a linked list. And so there's no branching out. So in the worst case, we're trying to remove the node just below the root. And that means that we're going to have to recurse n minus 2 times to get rid of the rest of the nodes. So the number of recursions is order n, and the complexity of the stuff we do inside each recursion is order n. So removing a node is actually an order n squared operation. Finding a particular value in the tree is just a linear search, so this is order n. And converting the tree to a string is also order n, because here's where we iterate over all the nodes in the tree, and that means that we're going to have an order n conversion to the string, where n is the number of nodes in the tree. To recap, in this lecture, we got even more practice doing algorithm analysis. In this lecture, we'll look at a number of different ways that we can traverse a tree. Specifically, we'll look at 3 different kinds of depth-first traversal. We'll look at pre-order traversal. We'll look at in-order traversal. And we'll look at post-order traversal, and we'll also look at breadth-first traversal of a tree. This is the tree that we'll be traversing, and I snagged this tree from the tree traversal page on Wikipedia, so you can compare our results with those on the Wikipedia page if you'd like to do so. This is a binary tree, so each node can only have 0, 1, or 2 children. To support this lecture, I implemented binary tree node and binary tree classes, so if you download the lecture code for this lecture, you can see how that works. We regularly talk about left child and right child for each node. We don't have a list of children, we just have a left child and a right child. Okay, let's go see how these traversal techniques work. In the main method of our lecture code, the first thing we do is we call a method that I wrote to build the tree that I showed you a picture of, and then we're going to demonstrate the pre-order traversal by calling the pre-order traversal method, and then we'll do an in-order traversal, a post-order traversal, and then we'll do a breadth-first traversal as well. So let's take a look at the pre-order traversal. The pre-order traversal method is pretty straightforward. First, we check to make sure the node that was passed in, and I'm calling this parameter tree because it really is a tree that is rooted at that node. So we make sure the node that was passed in isn't null. That will be our indication that we should stop recursing. We process the node first, and by process here, I just mean we write the value of the node, and then if the left child isn't null, we recursively call this method with the left child, and then if the right child isn't null, we recursively call the method with the right child. So this is using recursion to do a traversal of the tree. And the pre-order part of the traversal means that we do the node, then we do the left child, then we do the right child. So for the graph that we're traversing, you can see that node F is marked as 1, so we process node F, then we recursively call the method on the left child, so here we are at node B, and we process that node, and we recursively call the method on the left child, so we get to A, and we process that, and then we return from this recursion, and now we call the method on the right child, so we do D, and then we recursively call on the left child, so we have C, on the right child, so we have E, and then we back up all the way through these recursions back up to our root, and that was just processing the left subtree, so now we process the right subtree. So we first get to G, and we process G, and G doesn't have a left child. This is actually a right child of G, so we will immediately process the right child, and that's I, so we process the node, and then we go do the left child. When I run the code, if you look at the output of the node values in the pre-order traversal, that is exactly what I said it would be as we walked our way through the picture. So a pre-order traversal means we do the node, then we do the left side, then we do the right side, and we do that recursively. For an in-order traversal, we traverse the left child first, then we process the node, then we traverse the right child. So we don't do the node at the beginning here, we do the node between the left child and the right child. For the graph we're processing, as you can see, we go as far down on the left as we can. So we process A first, and then we do B, the node, then we work our way down the right side, but once we get to D, remember we do left first, so C is next, and then the node, and then the right side, and then we come all the way back up, so we already did all this stuff on the left, so we now process F, and we do the same thing on the right-hand side. Running the code again, if you look at the in-order traversal output, that's what I just said. And by the way, these are now in alphabetical order from A to I. And for the last depth-first traversal technique, we'll look at post-order traversal. And the difference here is we do the left side, then we do the right side, then we do the node. So again, we go as far down as we can on the left side, so we do A, and then we move up through B to D and go down on the left side, so we do C next, then we come up to D and back down and do the right side, and then finally we do D, and now we've done the left and the right side of B, so we come process B, back up the root. Now we're going to do the right side before we process the root. So we come down here and we can still do the right side before we process G, and we can still do the left side before we process I. So left side of I and back up here, and I doesn't have a right child. So now we just process I. And back up to G, and we've done the non-existent left child and the existing right child, so now we can process G. And now, because we did the left side of the tree and the right side of the tree, we can finally process the root. And this time you should look at the post-order traversal output and see that that is the order that I said this would be in. And those are the three depth-first traversal techniques. And you should have recognized them as depth-first because we were working our way as deeply down the tree as we could before we were doing things. We do have a breadth-first traversal technique as well, where we'll process the root, and then we'll process everything one step away from the root, and then we'll process everything 2 steps away from the root, and so on. I implemented the breadth-first traversal method using the technique that we used before when we were searching a graph, so I have a search list here. I don't need a path, I'm just going to process each node, so this is a little more simple than looking for a path through the graph, but I am using a search list, and I'm adding to the end of it, and I'm adding to the end of it because I'm doing breadth-first search. And I'm just going to process that search list. And each time I'll pull the first thing off the front of the search list and I'll process it. And if there is a left child, I'll add it at the end of the search list. And if there's a right child, I'll add it at the end of the search list. And remember, this was the difference between depth first and breadth first search. In depth first search, if we're using a search list, we add to the front of the list. But because we're doing breadth first search here, I'm adding new nodes to the back of the list instead. So this picture should not surprise you. We process F first, then we process B and G, those nodes that are 1 step away from F. Then we process A, D, and I, the nodes that are 2 steps away from F. And then finally, we process C, E, and H. And as you can see for the output for the breadth-first traversal, that is exactly the order that I said it would be in. To recap, in this lecture we saw a number of different ways to traverse a binary tree, and we also saw numerous examples of recursion in the depth-first traversals that we implemented. In this lecture, we'll learn about minimax search. What is minimax search? It's a technique to pick the best move in an adversarial 2-player game. Why do we care? Because this is a big help when we're developing artificial intelligence in a turn-based game. Let's look at an example. This example comes from Data Structures for Game Programmers by Ron Penton. He uses rocks, but of course I'm using teddy bears. So the idea behind this game is that you never want to take the last teddy bear. On your turn, you are allowed to take any number of teddy bears from a single bin, and you have to take at least 1 teddy bear. So this tree is rooted at the configuration shown at the top with 2 teddy bears in the left bin and 1 teddy bear in the right, and it's player 1's turn. And the next level of the tree, and this is often called a ply, like in plywood, there are different layers of wood. This is a ply in the tree. So 1 step down is all the different configurations that could occur from player 1 taking their turn. So on the left side, we have player 1 taking 1 teddy bear from the left bin. In the middle, we have player 1 taking 2 teddy bears from the left bin. And on the right, we have player 1 taking 1 teddy bear from the right bin. So to generate our minimax search tree, we're basically going through the different game configurations that occur as people take turns. Now it's player 2's turn, and on the left subtree, you can see player 2 can either take the teddy bear from the left bin or the teddy bear from the right bin. In the middle, the only thing player 2 can do is take the single teddy bear from the right bin, and that leads to player 2 losing because player 2 lost by taking the last teddy bear. On the right-hand side, player 2 has 2 choices. On the right-hand side, player 2 can be particularly stupid and take both teddy bears out of the left bin, thereby losing the game. Or they can take 1 teddy bear out of the left bin, and then on the next ply down, it's player 1's turn, and either they've won in that middle subtree or all the way on the right, or they have a configuration that only contains one teddy bear, so they're going to have to take that teddy bear, which leads to them losing the game. So this is the game tree for a complete play of Don't Take the Last Teddy. That's the new name, and that's the programming assignment for this module. You'll, of course, extend what we're doing here. But once we have the game tree, we need to help player one figure out what they should do for their turn. Now I've marked the game tree with minimax scores, so at the very top, at the root of the tree, player one is the maximizing player. They want to get the highest score possible, so the way we're applying minimax scores down on the leaf nodes of the tree is if player one lost, they get 0, and if player two lost, they get 1. So player 1 wants to make a move from the root that gives them the best chance of scoring 1. Player 2 on the next ply down is a minimizing player. They want to try to minimize the score that player 1 can achieve, so they'll make the worst move for player 1. And then the next ply down, player 1 takes their turn and they're trying to maximize their benefit, and so on. So that's why this is called a minimax search, is because we're alternating between minimizing and maximizing, even though we start with a maximizing move. Even though I've marked the game tree all the way up to the root, we need to understand how that works. So assume that I have now marked all these leaf nodes with the appropriate scores, and we'll see in the next lecture that we implement this with recursion. So now we back out of the recursion on the maximizing apply just above those bottom leaf nodes. So here, as we back out of the recursion from player 1 lost, player 1 picks the maximum score in all its children. It only has one child, so it just has to pick 0. 0 happens to be both maximum and minimum, but it picks the best number. It also does this on the next subtree, and again, no choices. This one, we're actually lucky. Player 1 is going to score a 1 at this ply of the tree. Here, player 1 picks the maximum of all its one child, so it has to be 0. And here's another place where player 1 wins. So we're backing up out of the recursion from doing our minimax search, and we just did the max level. So now we need to do the min level. So the minimizing player is going to pick the lowest score of all its children. Now on this left subtree, they're both 0, so it picks 0. On this middle subtree, it only has one child, so it has to accept that score. And finally, we see an actual decision. So the children have scores of 0 and 1. And because we are on the minimizing ply, we pick the lowest score between 0 and 1, so we pick 0. Because remember, player 2 is trying to do whatever is worst for player 1. But now player 2 is done, this level of the recursion is done, and so we back up to the root, and player 1 will decide between these three children. One child has a score of 0, one child has a score of 1, and one child has a score of 0. So player 1, because that player is a maximizing player, picks the highest score of the children, and that's a 1, and that makes it clear that player 1's next move should be to take 2 teddy bears out of the left-hand bin. Don't lose sight in the mechanics of figuring out how all this works. Our end goal is to tell the root of the tree, what should you do? And of course, that means that this is great for AI, right? We're trying to help AI make decisions. But that's how the minimax process works in this small example. To recap, in this lecture, we learned about minimax search. In practice, we usually limit the depth of search that we perform because in most cases, the fan out, the branches out of a particular game state are so high that we can't go all the way to the end of the game. So what we do is we limit the depth of our search and we use something called a heuristic evaluation function to assign a score based on whatever criteria we come up with for a particular game configuration. Common, more advanced techniques like alpha-beta pruning and iterative deepening are built on top of minimax search. So alpha-beta pruning is a technique that uses minimax search, but when we start exploring a branch that has no possibility of being better than our current best solution, we just prune that branch and we don't explore it anymore. Iterative deepening is a technique where we perform minimax search to one level and save that result, then perform minimax search to 2 levels and save that result, and so on. And this is a really useful technique when we have time constraints on how long we can execute the search. So in our Peak Game Studios game Cat, we actually used iterative deepening because based on the selected difficulty, the AI could spend a certain amount of time looking for their next move. And if we used iterative deepening, which we did, we could actually always have some solution when time ran out, but we could keep looking for a better and better solution until time ran out. In this lecture, we'll implement the minimax search for the example from the previous lecture. As a reminder, here's the search tree with minimax scores attached to those nodes. Let's go look at how we actually implement this. For our tree, we're using a modified version of the tree node and tree classes that we've seen before. The difference is that I've added a minimax score field to the tree node. And I've added a property that lets us retrieve that minimax score and to also set that minimax score. So this way the tree nodes can hold their minimax score as we do the minimax search. I've also added a configuration class that is essentially a configuration of the game board. I put board in quotes there. It's the bins and how many things are in each bin. So it's just a list of bins, each of which is an int, the count of how many things are in that bin. We have a constructor, we pass in the bin contents, and then we just add those contents to our bins list. We can get a read-only list of the bins. And this is a useful property to tell if the bins are empty because that means that the game has just been lost. So all we do is we go through each of the bins, and if the bin value is greater than 0, there's something in it, so we return false out of the property. If we get all the way past the loop, we never found a bin that had something in it, so we return true because the configuration is now empty. Over here in our main class, I have a couple of static fields that I'm saving for efficiency, and this is just so I don't need to keep creating new lists of ints and configurations. I can just clear these lists instead of creating new lists, and we'll see where I use both those fields soon. In our main method, we build the game tree, and then we run our minimax method to attach scores to each of the nodes in the tree. After we're done doing that, we retrieve the children of the root. We say the max child node is the first child. So what we're doing is we're assuming that the leftmost child is in fact the best choice, but we might find out we were wrong. So we go through the rest of the children. Notice we start this for loop at 1. And we check to see if that child's minimax score is greater than the max child node we've saved so far. And if it is, we just found a new max child node. So we set max child node equal to the one we're currently looking at. When we're all done, all we have to do is say the best move is to configuration max child node value. So this piece, just finding the best child node, is pretty straightforward, as is this. these are the pieces that are minimax search. To build the tree, we start by building the root node. So we have that bin contents list. I clear the list, I add 2, and I add 1. So that's the left bin and the right bin. And then I create a new configuration, which I've called the root configuration, and I pass in that list. So now root configuration is a configuration object that has 2 bins whose contents are 2 and 1. Now I need to go through and build the complete tree. So here's my tree, and the constructor for the tree requires that I pass in a configuration, so I do. I also have a node list, and I'm sort of using this like the search lists we've seen before. So I'm going to add a node to the list, and I'll pull a node from the front, and I'll expand its children, and I'll add them to the back, because I'm just going to do a breadth first build of the tree. And once the node list is empty, I'm done expanding nodes, and I've built my entire tree. So I add the root to the node list. And while there's something to expand in the node list, I pull off the first node and I remove it from the node list. I now generate its children by calling the getNextConfigurations method that we'll look at soon. This is the method that says, given this current board configuration, what are all the next possible board configurations? And it returns that to us as a list of those configurations. And then for each one of them, I create a node from that configuration, and I add that node to the tree, and I add that node at the back of the node list, because I'm going to want to expand this configuration to all its next possible configurations until I run out of configurations. When I'm all done, I return the tree. The game tree has been built, but there are no minimax scores attached yet. Here's that method that generates all the next configurations. So here's what I do. I get the bins from the current configuration, and I'm going to go through each bin. So I'll start at the leftmost bin, and I set current bin count to be whatever is in that leftmost bin. And while current bin count is greater than 0, I'll take 1 teddy out of the bin, and then I'll clear the contents and add the range of current bins. So I'm copying the existing configuration right here, and then I change the one I just changed, and then I add that new configuration to the list. So basically this inner while loop for a particular bin, it takes out 1 at a time, creating new configurations, and this for loop does that for each of the bins we have. In this particular case, we only have 2, but in your programming assignment, you'll have more than 2. Okay, so now the minimax search stuff. We pass in a tree, which is really a node, but it's a root of a subtree that we're going to search. And we tell whether or not we're maximizing, because that will determine whether we're trying to pick the highest score of our children or the lowest score of our children. Now I get all the children from this node that I passed in. If I have 1 or more children, then I'm going to loop over those children, and for each one, I'm going to make a recursive call to minimax with that child, and I toggle maximizing, because as I move down 1 ply, if I'm currently maximizing, I should be minimizing. And if I'm currently minimizing, I should be maximizing. So that's an important piece of doing this. As we move down, we have to change whether we're maximizing or minimizing. Once I've done all that, I set my beginning minimax score. So if I'm maximizing, I say the best score I've found so far is the minimum possible integer. So the first time through this loop we're going to get to, I should replace this with something better. Now I go through all the children of this node, and if I'm maximizing, I check to see if the child I'm examining has a better score than the best score I've found so far. And if it does, then I'm going to change the best score I've found so far to the one I just found. If I'm minimizing, I use less than because I'm looking for a worse score. Finally, if I'm at a leaf node, leaf nodes are the base case for our recursion for this example, then I assign an actual score. So up to this point, all we're doing is comparing scores and picking the best one, but we haven't actually assigned those zeros and ones to the leaf nodes yet. So assign minimax score does that. We pass in a node and we pass in whether or not we're maximizing. If in fact the configuration is empty, then if we're maximizing, if we're at a maximizing ply when we got to empty bins, that means that the minimizing player, player 2, took the last teddy. So we set our score to 1 because we just won the game. If we're minimizing, then player 1 took the last teddy on the previous ply, and we set the minimax score to 0 because player 1 just lost the game. And that's it. That is the code to implement a minimax search on the example we've been looking at. To recap, in this lecture, we learned how to implement a minimax search, and you'll actually extend this for the programming assignment for this module. What will you learn about in the design patterns lesson? You'll learn what a design pattern is, and it is a design that we use to solve a common problem in software. So we see these patterns of behavior that we need in our software, and there are good designs for addressing those patterns. And so a design pattern is like a template that we can use to design a solution to a particular problem in our software. We'll learn about a number of different design patterns, and we will see how those design patterns apply to games. There are a couple of great design pattern books that I wanted to mention, even though you don't need these books to complete the work in this week. The Nystrom book is a really entertaining read that has lots of great game development specific examples. And the Gamma book, which is regularly called the Gang of Four book because there are 4 authors, is really the standard design pattern book in software engineering. In this lecture, we'll look at the game loop and update method patterns. The motivation behind the game loop pattern is that we want to decouple the progression of game time from user input and processor speed. So remember, games are simulating a world, right? And time passes in that simulated world, and we want to make sure that the passage of time in our game world is not dependent on when the user provides input, or even worse perhaps, how fast the processor is. So some early games did not take processor speed into account. So if you ran the game on a processor that was twice as fast as what it was developed for, the game ran twice as fast. And we don't really find that acceptable in the game development domain, at least anymore. So the game loop helps us decouple from both user input and processor speed. Here's a description of the pattern. So we have a game loop that runs continuously, and it processes user input without blocking. So whenever that happens, it happens. It updates the game state, and it renders the game. It keeps track of passage of time so that it controls the rate of gameplay in the game. And we pretty much see the game loop pattern in every game. I understand that this picture is pretty much unreadable, but you can actually get to this picture and a deeper explanation of each of the boxes by Googling monobehavior lifecycle. So this is a demonstration of the game loop in Unity plus some extra stuff. So this loop part that I've highlighted is actually the game loop pattern. The motivation behind the update method pattern is that we want to take a collection of independent objects and we want to simulate them in the game world by having them each execute one frame of behavior at a time. So here's a description of the pattern. So we have a game world that holds a collection of objects. The Unity engine holds all the game objects in a particular scene, and then each of those objects are updated each update of the game. And of course, the physics engine will keep running the physics whether or not we implement anything in a script, but we can also implement both the update method and the fixed update method in a monobehavior script to provide additional processing either each frame of the game, which is where we put the update stuff, or on a fixed cycle of 50 times a second, which is the behavior that we put into the fixed update method. In this lecture, we'll look at the component pattern. The motivation behind the component pattern is that we want an entity, like a Unity game object, to span multiple domains, like rendering and physics, without coupling those domains together. Here's a description of the pattern, and to summarize, basically for each of the domains, like rendering and physics and so on, we provide one or more independent component classes, and then the entity is just a container of those components. This should all sound really familiar to you since we've been working with the Unity component-based system all the way since the first course in the specialization. So Unity game objects have components attached to them so that we can divorce the different domains from each other. So here's an example from the teddy bear destruction game from the second course in the specialization, and this happens to be the burning teddy bear, and we have a transform component that shows where this game object exists in the world. We have a sprite renderer component so it gets rendered appropriately. We have a collider and a rigid body so it can do physics things in the game, and we even have an additional script attached to provide extra behavior, and that's also a component. So this component pattern should feel like nothing new to you because we've been using it all along in Unity. In this lecture, we'll look at the prototype pattern. So to paraphrase the Gang of Four definition, we basically come up with a template for an object that we're going to create multiple instances of, and when we need an instance of that object, we copy that prototype. In practice, this should sound a lot like Unity prefabs to you. So basically, we build a prefab, right, with lots of characteristics, including components attached to that game object and so on, and when we need a new instance of that game object, we just instantiate that prototype. So really, Unity prefabs are an example of the prototype pattern. If we think about the way C# works as a language, we can also think of C# classes as prototypes because they form a template for the objects that we would create, and basically we instantiate the class to form objects. And so as a language construct, C# classes are also an example of the prototype pattern. In this lecture, we'll look at the singleton pattern. As the Gang of Four described the intent of this pattern, we ensure a class has only a single instance, and we provide a global point of access to that class. There is a very strong and reasonable objection to the singleton pattern, and that objection is that it provides access to global state, And in the software engineering community, people have recognized that global variables are a bad thing in general for maintainability and so on. So there is an alternative to the singleton pattern, and it's the static class, but there's a problem with static classes as well, because even though static classes, we know we only have one instance of them, and we know they provide global access to the class, that still doesn't keep people from changing whatever global state is held in that static class. Now, if we have a static class that exposes read-only information, that's perfectly fine from a good software architecture perspective. So our configuration utils, for example, when we were providing access to configuration data for a particular game, that configuration utils class was a static utility class that provided access to global game state, but it was read-only access. So that was perfectly fine. Sometimes, though, even a static class doesn't work. So, for example, if we want to attach a script to a game object, we can't attach a static class to a game object. So we may need to have some other approach to get the same ideas behind one instance of an object and global access to that instance. So let's go look at an example that we've seen before. Remember, this is not an implementation of the singleton design pattern. It is taking advantage of the beneficial ideas in that pattern without any of the dangerous stuff. So here we have our game audio source. And remember, this is the single audio source for the entire game. In the awake method, we check to see if the audio manager has not been initialized yet. Because the game object this game audio source script is attached to is in the main menu scene, we could return to that scene multiple times. Each time we do, awake will get called on the game audio source. So we need to make sure we only have one of these in the game. We don't want to create one every time we go to the main menu. So there's that piece of the singleton design pattern that says there's only one of them. We can tell whether or not we already have one by checking to see if the audio manager is initialized. And if it is, we already have one, which means this one's a duplicate game object, so we destroy it. If the audio manager isn't initialized, then we add an audio source component to this game object. We call the audio manager initialize method with that audio source, and then we say don't destroy on load the game object, which makes this game object persist across all the scenes in the game. In the audio manager, we have a field to hold the audio source, we have a flag to tell whether or not we've been initialized yet, and this other stuff is a dictionary of audio clips so we can play the appropriate audio clip when necessary. This is just the property we saw the game audio source script access to tell whether or not the audio manager has been initialized yet. This is the method that it calls, and we set that flag to true because now we have been initialized. We save that audio source into our field, and then we add audio clips to that dictionary of audio clips for all the sound effects that we might want to play as we play the game. Here's the other piece of the idea behind the singleton design pattern. Any other object in the game can call the play method with an audio clip name, and here the audio source plays the audio clip in the dictionary with the given name. And play one shot is a fire and forget. You just play it and then you can move on, which is great when you might want to be playing a bunch of audio clips at the same time with a single audio source. So this is the global access to the audio source object. But as you can see, there's nothing that any other object can do to sort of break our global state in the game, but we are providing global access to this audio source that we only have one instance of in the game. To recap, even though the singleton pattern has fallen out of favor, it is still reasonable to use variations of that pattern in particular situations. In this lecture, we'll discuss the observer pattern. According to the Gang of Four, this is a pattern that lets us build one-to-many dependencies between objects, so that when one object changes state, all those dependent objects are notified so they can do whatever they need to do based on that notification. This should sound really familiar to you because in practice, this is an event system. So the object that has a state that will notify the others is an invoker of an event, and the objects that care about that state change, that want to be notified when that state change occurs, are listeners for the event. So entire event systems are built around the observer pattern. In this lecture, we'll take a look at the mediator pattern. To paraphrase the Gang of Four description of this pattern, we basically develop a class, a mediator, that encapsulates how other objects interact with each other. And because those other objects don't refer to each other explicitly, that leads to loose coupling, which means those objects aren't tightly connected to each other. And we can also change in the mediator how those interactions actually work. In practice, we've seen this and we've implemented this in event managers, because remember, the event managers that we've used have made it so invokers of the events and listeners for the events don't have to know about each other. They just work through the event manager, which is the mediator that connects those different objects together. Let's go remind ourselves about how the event manager worked in the Feed the Teddies game. The big idea behind this event manager class, and any event manager class we're implementing, is really to make it so that the event invokers and the event listeners don't have to know about each other. So remember, the mediator pattern says that these objects don't need to refer to each other explicitly, and that's what the event manager does. It serves as the mediator to hook the invokers and listeners together. So we have a field of invokers and a field of listeners, and this is a dictionary of event names and the list of invokers for that event name, and an event name and a list of listeners for that event. So we can have multiple invokers for an event, and we can have multiple listeners for an event. In this lecture, we're not worried about the initialization stuff, because here's the real mediator stuff. When we call the add invoker method, we provide the event name and the invoker for that event. And for each of the listeners, we add that listener to the invoker that's being added. So this is great because the invoker doesn't have to maintain a list of people who have said they want to listen for it. The event manager does that. And then, of course, we add the invoker to the dictionary of invokers for the given event name. Adding a listener is even better from the mediator pattern perspective, because when we call this method, we provide an event name and the listener, and we go through each of the invokers for this event name and add this listener as a listener. And this means that the class that holds that listener delegate doesn't have to know about all the objects that are currently in the game that might invoke this event. So this decouples or provides loose coupling between the invokers and the listeners because they don't have to know about each other. The event manager takes care of all those details. To recap, in this lecture, we saw how the event manager in the Feed the Teddies game implements the mediator design pattern. In this lecture, we'll explore the object pool pattern. So the motivation behind this pattern is that we improve performance and memory usage by reusing objects from a pool instead of allocating and freeing those objects individually. And those terms, allocating and freeing, sound a lot like C++ terms where we have to manage our own memory, but this applies in the C# domain as well, where we instantiate objects, and then when we're done with them, the garbage collector picks them up. The object pool pattern applies in the C# domain as well. So, adapted from Nystrom's description, we define a pool object that holds these objects that we're going to reuse. When we need one, we ask the pool for it, and when we're done with one, we return it to the pool. Let's go implement the object pool pattern for the French fries in our Feed the Teddies game. Because we're going to pool the French fries in this game, we actually need to make some changes to both the French fries and the burger classes. So we'll look at those first, and then we'll look at the French fries pool. Here in the French fries class, we're going to initialize the object, and I used to do this work in start instead of initialize, but I want to initialize the French fries when I'm creating them and putting them in the pool. And if they haven't been added to the scene yet, then start won't get called. So I'm going to call this initialize method explicitly when I instantiate a French fries object. I also used to start the French fries moving in the start method, but now what we want to do is we want the burger to grab a French fries object from the pool, put it in the place where the burger is, and do any other work it needs to do, and then start the French fries moving. So we needed an explicit method that we could call to actually get the French fries moving. And we want to stop the French fries moving when we actually put them back into the pool, so that the next time the French fries are removed from the pool, they don't have any velocity. Anytime we destroy the French fries, instead of actually destroying the game object the French fries script is attached to, which is what we used to do, we're going to return the French fries to the pool instead. So now French fries will be a reusable object that we can just retrieve from the pool when we need one, and then return back to the pool when we're done with it. So this is a change because we're not destroying the French fries game object, we're returning it to the French fries pool. And that applies in the other places where we used to destroy the French fries as well. And those are the changes to the French fries class. In the burger class, we've removed the prefab for the French fries that we used to have, and instead of instantiating that prefab here, instead what we do is we get a French fries object from the pool, we move it to where it should be. We set it active because now the French fries are active in the scene. And we also get that French fries script that's attached to the game object and call the start moving method so that the French fries actually start moving. So those are the changes that we need to make to French fries and burger. Let's actually look at the implementation of the pool itself. We have two fields in this class. We have the prefab that will instantiate, and we have a list of game objects that is the pool of those French fries. We have an initialize method that gets called by our game initializer script, and that happens in the main menu scene. So we're going to initialize our pool while we're essentially waiting for the player to interact with the menu, and that's a good thing. So the first thing we do is we load the prefab French fries as a resource. I moved it in the Unity editor to be a resource. And now I create my pool. And we'll start for demonstration purposes by creating a pool with a capacity of 2. So this constructor for a list, we provide the capacity, and that keeps us from having to keep growing that list. Remember, growing the list is an order n operation, so we want to avoid that. Clearly 2 is not the right choice for our pool, so I'll increase that number when I do this in practice, but I wanted to show you that the pool actually grows, which is also an important thing. Okay, so this for loop, I start at 0, I go up to the capacity of the pool, Notice this is not count because there's nothing in the pool. This is capacity because I want to completely fill the pool I just created. And I add a French fries object that I get from the getNewFrenchFries method that we'll look at the very end. So this initialize method basically just fills up the pool. The getFrenchFries method is the method the burger calls when it needs a French fries object to fire. The first thing we check is to see if, in fact, there's something in the pool. Because if the pool is empty, we're going to have to do something else. But if the pool has at least one object in it, then we'll use that object. I'm going to retrieve the object that's at the end of the list because we know that remove_at is a constant time operation if we're removing from the end of the list, and then I return those French fries that used to be at the end of the list that is our pool. If the pool is empty, this is the message we'll see, and of course you don't keep that in an operational game, but this is just to show you how this is working. So what we're going to do is we're going to do two things. First, we're going to expand the capacity of the pool because we want the pool to be larger now. We know it needed to be larger. And I'm just going to add 1 to it, and we'll see why in a couple of minutes. But I want to increase the capacity so that if all of those game objects that have been either in the pool before or that we're creating right here are put back into the pool, that we don't have to expand the pool. So again, we're avoiding that order n operation of growing the pool. So I increase the capacity, and then I return a new French fries object. We're almost to the point where we'll look at that method. The other thing is that when a French fry is destroyed, it returns itself to the pool. And so this was the method that we saw getting called in the French fries class. We do a number of things. We set the French fries to inactive. That's why we provide false here. So it's no longer an active game object in the game. We stop the French fries from moving, and we add the French fries back into the pool. And that always gets added to the end of the list. And remember, that will always be constant time because we expanded the capacity as we needed to. So the capacity of the list is always the same as the total number of French fries objects that are in the game. Here's that method I keep talking about. So we instantiate our prefab, and then we call the initialize method that we already looked at. We set active to false because this is not an active game object. We say don't destroy on load, and I will admit that this was a bug that I had to figure out. So remember, game objects are destroyed as you move from scene to scene in the game. And because I was loading up the pool in the main menu, by the time I got to the gameplay scene, all those French fries objects had been nulled out because the engine had destroyed them. So just as we saw in our game audio source in Feed the Teddies, if we want a game object to persist across scenes, then we call don't destroy on load on that game object. So that was an interesting bug to figure out, but luckily I figured it out. And we return to French fries. So that's the implementation of our French fries pool. I'll show you it in action momentarily, but I did want to say, if you Google Unity object pool, you may find tutorials that say this approach is wrong, that it is wasteful and time-consuming, and what you should do instead is just build a pool of objects and basically mark those objects as active or not. And when you need a new object in our getFrenchFries method in this example, then you do a linear search on that list to find an inactive object to return. And that's a bad idea because we know linear search is order n. And so as our pool gets huge, that search to find an available object takes longer and longer. So let's look at the complexity of this implementation instead, since I said it's better. We know this is constant time, this is constant time, this is constant time because we're removing from the end of the pool, and this is constant time. This is constant time. This wouldn't be included in our real game. So the only question is, what about this? What about increasing the capacity of the pool? If that's constant time, that's great. Getting an object from the pool is always constant time, which is better than order n. If it's not constant time, then we maybe haven't done anything to improve that other approach. Here's the documentation for the list capacity property. And at first blush, this is not a win, because it says here, setting the property is an order n operation where n is the new capacity. So if in fact that statement is true, then we haven't done anything better than the other approach. This is a little ugly to have to do, but that didn't make sense to me when we're increasing the capacity of an empty list, which is what we're doing. We only execute this code if pool.count is equal to 0. So when things don't make sense to you, given your understanding of how everything works, it's reasonable to explore further. So it turns out that Microsoft gives us the source code for the list class. And if we look at the source code for the capacity property, and we look at the set accessor, and we don't worry about the contract stuff, value, the new capacity, is not equal to the old capacity. That's certainly true. If value is greater than 0, and of course it is in our case, then it creates a new array of the appropriate size, which makes perfect sense. Here's the piece that says we don't have to worry. If in fact count, because they use underscore size to keep track of count, if that's greater than 0, it does an array copy. And this is where you get order n. But it's really not order n in the capacity, it's order n in how many things are currently in the list. And they made a reasonable assumption when they provided the complexity of this operation in their documentation. They assumed you would only increase capacity when your list was full. And we're actually increasing the capacity when our list is empty because we know we need that capacity later. So this Boolean expression, in our case, evaluates to false. So all that happens is this. So actually for us, increasing the capacity by 1 is a constant time operation. So that means that increasing the capacity is constant time for the way we're doing it, because we're only doing it on an empty list, which means getting an object from the pool is constant time rather than order n. If we were in fact paying a price when we return objects to the pool, then we haven't won over that other approach either, but this is also constant time. So setting active is constant time, stopping moving is constant time, and because we made sure that the capacity is as big as the total number of French fries that are floating around in our game, add is a constant time operation, not order n, which we'd have to pay if we had to expand the list. But we don't have to expand the list, so this is constant time. So this implementation of an object pool is constant time for getting an object from the pool and returning an object to the pool, and that's better than the order n object pool implementations that you might see as you wander around the web. So if I play the game, you see I don't get any messages as long as I only use 2 French fries. But as soon as I need a third French fry, you can see that I need a pool, and I can go to pool again if I need a 4th French fry, and so on. So of course you wouldn't include this message in a game that you shipped, but I wanted to use it to show you that we actually do grow the pool as we need to, as we need more French fries in the game. To recap, in this lecture we learned about the object pool pattern, and we implemented that pattern for the French fries in our Feed the Teddies game. In this lecture, we'll look at the state pattern. To paraphrase the Gang of 4 definition, this lets an object change its behavior based on its internal state. So it looks like the object is turning into a different class because its behavior has changed, even though it's not actually changing classes. The way we actually implement this pattern in practice is typically using something called finite state machines. Let's look at a couple examples. This is a finite state machine for a player in a platformer. So the circles are different states the player can be in, so they can be standing or walking or jumping or falling. And the way we move between those states is we follow one of those arrows, those edges, that are called transitions. And really the way this happens in practice is the transition is caused by some event. So we transition from walking to jumping by pressing the space key. And we transition from jumping to falling when our vertical speed becomes greater than 0. The way we would implement this finite state machine is usually with a switch statement or an if, else if statement that actually says, if I'm in this state, here's how I behave. If I'm in this state, here's how I behave, and so on. That's one of the common ways that we would implement a finite state machine. Here's another example of a finite state machine, and this is a horribly stupid enemy NPC. So think of this as a 2D game because I'm talking about the number of pixels here, but it could certainly be world units in Unity as well. And that's really probably how we would implement it even in a Unity 2D game. So I'm wandering around as an enemy, and if the player gets within 200 pixels, I start chasing the player. But if I get close enough, if I get within 100 pixels, then I start running away. And after a second, I decide that I've forgotten that I was scared of the player, and I start wandering again. The point is not that this is a fantastic enemy NPC that you should implement in your RPG. It is instead another example of how we express states and remember different behaviors in each of those states. For example, when the enemy NPC is chasing the player, he's moving toward the player. And when the enemy NPC is retreating from the player, they're moving away from the player. So the behavior of the enemy depends on the state that the enemy is in. To recap, in this lecture, we saw how we can use finite state machines to implement the state pattern. And I will say that finite state machines are particularly useful when we're implementing artificial intelligence in our games. In this lecture, we'll look at the strategy pattern. To paraphrase the Gang of Four, we take related algorithms, encapsulate each of them, and make them interchangeable. What that does for us is it means that we can change the strategy without changing whatever object is using that strategy. In practice, in our Battle Paddles game, we actually have AI that can be either offensive or defensive or balanced. And we implemented those as 3 different strategies, and the mechanism we used for that is inheritance. So they were interchangeable because they all had the same parent class, but we had different behaviors, different strategies in each of those balanced offensive and defensive strategic objects, the child classes. We also have seen an example of the strategy pattern with our homing component in the Feed the Teddies game, because we could take that strategy, a way of behaving, and attach it to multiple game objects. We attached it to teddy bears and teddy bear projectiles. And so we could use the same strategy for multiple objects. And that's also a really useful way to take advantage of this pattern. In this lecture, we'll look at the template method pattern. To paraphrase the Gang of Four, we basically build the skeleton for an algorithm, but some of the steps we leave up to the subclasses to implement. So different subclasses can implement different pieces of the algorithm without changing the overall structure of the algorithm. In practice, let's go remind ourselves about how we did this in the teddy bear destruction game from the previous course. In our teddy bear class, which is the root of our class hierarchy, here's where we see the template method pattern. And usually the template method appears inside some other processing, so that's why the pattern talks about not changing the structure of the algorithm while providing a piece of processing in that algorithm. In this particular case, all we're doing is we're responding to on-mouse enter, and we're doing subclass specific processing inside that method. So this is a template method example where process mouse over is the template method. That's why it's defined to be abstract, because the subclasses have to plug in the template method processing for the subclass. Our disappearing teddy bear simply adds the points for the teddy bear and destroys the teddy bear. Our exploding teddy bear adds the points for the teddy bear, instantiates an explosion, and destroys itself. And the burning teddy bear does some more complicated stuff by starting itself burning only if it's not burning already. So these three subclasses implement their own versions of the process mouse over method to provide subclass specific processing, and that is the template method, where the template method is plugged in here inside the on-mouse enter method in the teddy bear class. To recap, in this lecture we saw how we implemented the template method pattern in the teddy bear destruction game. Great job making it to the end of this course. If you did the previous 3 courses in the specialization in addition to this one, then you've basically completed the first 2 programming courses I teach at UCCS. If that's all you need and you want to go build your games, then by all means do so. You're 4/5 of the way through the specialization, so I encourage you to take the next course, the capstone course, where you get to build your own game. Whatever you decide to do, thanks very much for joining me in this course. I love doing these courses, and I'm glad you came along with me. Cheers.